Good morning to one and all. Welcome to the second day of 27th National Conference on Sensors and Automation. Let's have a look on today's agenda. Today's first session will be taken by Mr. Abhay sir. The second session will be taken by Dr. Ashwini Kotrashetty ma'am. The third session will be taken by Mr. Srinivas Kulkarni sir. Then there will be demonstration of project by the students after the session of Mr. Alistair De Silva sir. At 12:30, there will be a lecture by Mr. Sanil Darvi sir, and then there will be declaration of winners of e-poster competition. After that, there will be announcement of forthcoming conference and then vote of thanks. So let's begin with the second segment of this 27th National Conference on Sensors in Automation. Now, I would like to request Mr. Tushar Mohite Patil sir, Head of Department, BPM's Polytechnic and Organizing Secretary of today's conference to introduce our today's speaker. Sir.
Thank you, Pooja madam. Am I audible?
Yes, sir.
Good morning, all of you. It's my pleasure to introduce such a knowledgeable and eminent personality, Mr. Abhay Phansikar. He will be giving the first talk of the today's session. It's my pleasure to read his profile. So he is a senior member of IEEE. He has experience of nearly 30 years in the field of product development, embedded solutions, technical marketing, and turnkey offerings. He has developed systems which includes mission critical military grade systems, air traffic control simulator, radar tracking systems, healthcare, ERP, and portals. He is also associated with the education. He is on the advisory boards of the engineering colleges. He goes as a project examiner. He undertakes lectures for skill and knowledge development and faculty development. He is a visiting faculty on cloud computing and advanced data structures, algorithms, and object-oriented software engineering. He has performed a variety of roles, which include director, president, and COO, chief technical architect in Indian and international organizations. He is a well-networked person in the industry. His interests are in providing strategic directions to startups and growing organizations. He is a past chairman of IEEE Bombay section and also a mentor on Startup Bootcamp, one of the top 3 global accelerators for startups. He is currently the consulting program manager for a multi-location development of practice management, EMR healthcare applications with over 200 clients. He is a consulting director for hospitality domain organization, helped scale services business in USA, Europe, setting up practice verticals and setting up channel partners globally. Between 2010 and 2014, he was a corporate strategy consultant, helping organizations achieve their growth target and creating a scalable infrastructure. Between 2006 and 2006 to 2010, he was a core project and technology. He was in core project and technologies. It is a listed $150 million education solution organization. He was there on the position of president for UK, head pre-sales, CEO global, and head ODC. During 2001 to 2005, he was in Rave Technologies Limited, the $10 million outsourced product development organization. The position held by him was he was a vice president, senior consultant, head of IT and technical services. During 1999 to 2001, he was in Mahindra British Telecom, $150 million software services organization. The position held by him was the Group Head Excellence Center. Between 1996 to 1999, he was in Onward Technologies, a listed $10 billion software services and networking organization. The position held was he was business manager and senior manager. During 1984 to 1995, he was in Tata Power R&D, a $1 billion division of organization. His position held was senior executive engineer. So today we have with us Mr. Abhay Phansikar, and we are eagerly waiting for his talk. And I'm sure all the students, they will enjoy this talk. Thank you very much. I request Mr. Abhay Phansikar, sir, to start his talk. Thank you.
Thank you, Dr. Tushar, sir. I will share my screen now. And just, are you able to see my screen?
Yes, sir.
Yes, sir.
Yes, sir.
And the next slides, they're switching?
Yeah.
Okay, fine. So today I'm going to talk on LoRaWAN. I'll give you a brief of that technology and why it is required, and the ecosystem that can be built around this. Since this conference is on sensors, I guess you will be exposed with various sensors. It could be MEMS sensor, like using all nanotechnology, or it could be biosensor, which will go in a body, or it could be regular temperature, pressure sensors, which could be used for very critical applications. So they could be like millimeter sensors, or there could be nanometer sensors. You have sensors of various kinds, depending on the application. And if we look at the sensors today that are probably likely to come in healthcare or those kind of things, where there will be sensors put in the body for monitoring or for control, there's a lot of security and other aspects associated with them. And with those sensors being very small and not having any processor, what kind of technology will work with those sensors? So that is something we may look at in future. So from a sensors perspective, all you know is that the sensor will collect some data and send it forward for processing. If it's a temperature sensor, it will monitor the temperature and then put it on its output pins. If it's a pressure sensor, if it's a gas sensor, all the sensors are doing is giving some readings. Now those readings have to be transported into the external system. And if we look at IoT today, they are saying that 25 billion connected objects in 2020. So if we are talking of these many objects, and today we have things like Fitbit that people put on their arm. Now, all of these objects have some or the other sensor. Your mobile phone has accelerometer sensor, a GPS sensor. Your Fitbits have similar sensors, and they also monitor temperature, your pulse rate. Now, all of these sensors are connected and they're transmitting. If you look at Internet of Things and applications, you will see that there are air pollution sensors, forest fire detection sensors. You have offspring care sensors. So people are actually putting sensors on kids, making sure that they're within the campus of the building. There are structural health sensors. So there are sensors on various roads and bridges to capture vibration. There are perimeter access control sensors. There are traffic congestion sensors. You have smart roads, smart lighting, intelligent shopping. All of these have various kinds of sensors in the industry. Now, all of these sensors require some kind of power and some kind of connectivity. So my talk today is going to be, if you have all these sensors, what are the problems that you will face and what are the technologies that in future will be required to overcome those problems. So if you look at the 25 billion sensors that are connected, and you make a project, you make a automation project, and you connect our normal cell phone battery for the sensors. Say you have a plant, an industrial plant, and you are trying to look at gas leaks, or you even have a building which has been built on reclaimed land, or some land which used to be garbage dump earlier but now has been flattened and nicely cemented with mud, tar, and all those kind of things. But below it, it used to be a garbage dump. I mean, since you are based in Thane, you would know that near the Mulund Thane toll naka, there have been these kind of areas which are now completely refilled and reclaimed. There are cases of methane gas that comes out over there. Now, these all areas are being monitored by people. And if you put these sensors, they require some kind of power. And if you're using a battery power, 400 milliampere hour battery, which we use for our cell phone, 4000 milliamp, you will require 500 gigawatts of power if those battery and the sensors are connected all the time. Imagine the amount of power that will be used if you are using our standard battery. Suppose you use a 1000 milliamp hour battery and you keep it on for 24 hours, you still require 125 gigawatts. Or you use a 150 milliamp battery, our normal simple cell, and you keep it on for 30 days intermittently, you'll still require 1 gigawatt of power. So it's not only the sensors that you should look at when you're building your solution, but also look at the kind of power they will consume. And if these sensors are transmitting, say, 100 megabytes of data per day, then you are talking of 2500 petabytes of data that is getting transmitted all throughout the day. And if you are sending out 1 kilobyte of data, you're still talking of 25 terabytes. So imagine if your sensor is not very efficient, it is consuming a lot of power and it is consuming a lot of bandwidth on the network. You will be loading the network with these kind of problems. So there is a need for a new technology now. Smart cities and many other verticals cannot really take off with the current communication technologies. What you need is something different. So traditional cellular technologies are designed for broadband communication. So our Wi-Fi, our mobile phone GPS, GSM, CDMA, they all are basically meant for high data rate communication and high revenue per device. And the devices are expensive. They are unsuited to low cost, low data rate devices and applications. So if you are kind of putting sensors all across a city or all across your factory and using Wi-Fi or cellular technology, you will be paying a lot for maintenance. Your sensor might be very cheap, but the whole network will cost you very much. And also existing wireless technologies such as Wi-Fi or Zigbee are unfit for broad deployment or coverage. If your factory is, say, 1 kilometer across 1 kilometer, simple small factory in a 1 square kilometer area, you'll require hundreds of cellular networks and hundreds of Wi-Fi or Zigbee points, connectivity points to cover that kind of an area. Even 200 meter by 200 meter factory or a 1 acre land of area, you will require so many access nodes and so many data points that the cost of sensor becomes very, very minuscule and the cost of networks becomes very high. So to overcome that problem, you have now technologies which are LPWAN or Sigfox or Link Wraps. They all are now coming up. So you have to understand and appreciate that these technologies are very, very essential in your network deployment. So one of the technology that has picked up in a big way is LPWAN, LoRaWAN. It is low power wide area network. What does it do? The range between gateways and devices is 3 to 5 kilometers in urban areas and 10 kilometers in rural areas. So if you put one sensor or you put hundreds of sensors all across, you will need just one gateway, one connecting device in an area of 3 to 5 kilometers in cities. Okay. And the other advantage is this technology uses low bandwidth and low power. So the device's battery life typically is 10 years. And I'm talking of solutions that we have built. So I'm not talking of some theoretical applications. And these communication systems are optimized for low data rate connected objects, basically for sensors and actuators, and based on an emerging standard called LoRaWAN. So what does it do? It basically has looked at sensors, and we know that a temperature sensor will simply send the temperature. And if you're monitoring the temperature, say every 1 hour or maybe every 15 minutes, all you need to do is send very less amount of data, just the temperature value. And if you use a Wi-Fi or a cellular network to do that, what you'll have to do is, even though you're just sending, say, 10 bits or 12 bits of data, but for the network to be alive, you will be sending pinging packets every few milliseconds to tell the cellular tower that I am alive and I am connected. And you will be using a TCP/IP kind of protocol. So you will be building a lot of data overheads over that simple 10 bytes of actual data. You'll be putting IP addresses, you'll be putting network addresses, you'll be putting certain security information, you'll be putting certain encryption information, you'll be putting endpoints information and various connection protocols. I mean, you don't really have to configure, that all is pre-configured when you set up a network, but this is the amount of data that goes through it. So this LoRaWAN is a communication system optimized for low data rate connected objects. Okay. The other thing is, you also many a times require the location of the sensor in real time. Suppose if it's on a vehicle and the vehicle is moving, then you need to know where the sensor is, and if it is sending a temperature, it is of which region. So these sensors are not connected with GPS or other kind of things. They simply use something called as triangulation. So a triangulation algorithm will provide the location of the sensor, because you know the location of the gateway to which it is connected. And through that, you will be able to calculate and identify where the sensor is. And this system gives substantial advantages in terms of cost, size, and power over traditional systems. So here's a solution that we had put. This is a district in Zurich, Switzerland, which is a 4.5 kilometers area. And over there, we deployed this LoRaWAN network. So if you see, you'll see the outdoor gateway. It's a very small gateway, which we have mounted on some 2-3 buildings within Zurich. And we have made this sound pollution monitoring sensor. So if you look at the pencil and the blue square box on the right hand corner, you know that it's a very small sound pollution monitoring sensor. So it is catching the sound. We have put in a very small microprocessor. So we are doing some amount of processing also on that sound. And we are using our standard cell, battery cell. And these kind of devices are placed all over the city. So you don't require any power connectivity. You don't require any configuration to be done. So if I was to place them on 100 buildings, I'd have to configure with the local Wi-Fi in that building for data transmission, or I would have had to put a SIM card in this blue box for usage of cellular network. So this is what we are kind of doing. This whole network, we are able to set it up. And if you see, there are like 2-3 gateways that we have put in that area, and they are communicating very, very efficiently. And we are claiming that this battery cell will give a life of about 3 years. So once you put it, you can forget everything. So this is the great advantage of using a LoRaWAN kind of a network for your sensors. So what is LoRa? So LoRa is a disruptive technology that has come in, which is basically giving dramatic improvements for solutions that are required for IoT or automated meter reading. So all your power meters today, if they are connected with this LoRa sensor, you won't have to send some person to the home, and you don't have to worry about using any other technology to keep on changing the configuration. And it is giving you 10 to 50 times improvement over the current networks that are being used. So you use a sensor, you connect it via a LoRa chip, and you put a gateway, and you're done with. And this LoRa, if I were to talk of how much power does it take? So if you look at a typical wireless LAN, it says it requires 15 dBm of power, that is 32 milliwatts of power. And if you look at a GPS says minus 111 dBm. So 0.008 picowatts of power. So this technology is something that has been existing for some time. It is not new technology or some great discovery that we are making. We are using the technologies that are used by people in GPS kind of sensors. And then we are using those technologies for our advantage, for our communication. So a GPS is able to connect to a satellite with this low amount of power. So a LoRa WAN system typically works with minus 140 dBm of power. It is very, 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 very less. Okay, we are really talking of picowatts of power, not milliwatt, not microwatt, not nanowatt, but one level below that. But if you want to use this low power, where are you compromising? You're compromising on the data rate. If you see this graph, if you go to 140 dBm, you are basically talking of less than 1 kilobytes of data that you can send. If you are looking at, say, Zigbee or Wi-Fi, you're talking of minus 90 dBm of power, which is in milliwatts, which is like 100,000 times more than the power that is used by LoRa. But when you use Wi-Fi, you can get higher data rate. When you use LoRa, you will get a lower data rate. And this whole technology is built on something called as FSK, frequency shift keying. It is an existing technology which is being used by communication networks. So all our railway networks and all those things in olden days were using FSK and FSK modems. They are not very popular now, but this technology has been existing and in usage for a long amount of time. So we are simply using those things to reduce the power, to increase the distance of communication, and we are compromising on data rates. So this is where typically a LoRa network is operating. And a LoRa network demodulates at -20 dB below the channel noise. So if you have a very, very noisy channel and you send a LoRa packet on that, and the power is maybe say 1,000 times or 100 times lower than the power of noisy signal in that area, even then your system will be able to detect that signal. And why? Because we are using a spread spectrum waveform. We are not using a narrow waveform which all our Wi-Fi and other technologies use. So you require very sharp frequency for them to operate. You're simply talking that it will work in a very broad frequency area. So when you send a signal, the signal is not, say, 800 megahertz signal or 1600 megahertz signal or 1900 like the Wi-Fi use it, but it will be a signal that will be spread, say from 800 to 805 megahertz. So when that signal is spread across so many frequencies, there will be some frequency which will not have noise at a particular given point of time, and your device will be able to latch onto it and read the information. And since the information is very less, it will be able to read that information in a very small time slot also. So this is how that technology works. Very, very simple technologies that has been in use for a long period of time. And how does LoRaWAN get used? So LoRaWAN has three kinds of classes. So class A is used for battery powered sensors or actuators with no downlink latency constraint. So what do class A devices do? They simply transmit. They don't do any handshake, any communication with the network. Wherever they are, you simply set the transmission interval and they will keep transmitting at that point of time. So temperature sensor, if you set in transmission interval of say 15 minutes, so every 15 minutes it will transfer. It will not check whether I have a connecting signal and all those kind of things. It will blindly transfer. And the advantage is because you're using very, very low battery power, you can actually have that sensor transmit every 1 minute or 5 minutes also. And your end system will catch it. Your class B sensors are battery powered actuators. They are based on slotted communication synchronized with the network. So when you are having a class B sensor, it will transmit at a given interval and it is actually doing some handshake with the network. So class A sensors are using very low power, class B sensors are using medium power, and class C sensors are mains powered actuators. They are devices which can afford to listen continuously. So when you create a gateway, your gateway will be a class C device because it will be required to be continuously on and in a continuous receiving mode, transmitting mode, and that is a class C. So LoRaWAN, you have the advantage that based on your application, you can make a class A, class B, or class C device. And typically when you see this, you have the devices, you can connect them to a nano gateway. So if your network is within a campus or a factory, say 0.5 kilometer by 0.5 kilometer factory, You can use a nano gateway, a simple small gateway, and all the LoRa devices will communicate with that. If you have a slightly larger factory, you will need something called as a micro gateway. So nano gateway could be a class B kind of an application. Micro gateway is class C application, or you need a telecom gateway. So if you have this municipality, suppose Thane municipality wants to connect all the electricity meters in Thane on LoRa, then it will require hundreds of gateways to cover every 2 kilometers worth of area, and a lot of power for the gateways. But the devices which are going to go in the automated meters will be very small devices running on a very small pencil cell battery. I mean, something that goes in your watch also. So you can use a watch battery, the round one, with low power, and they will communicate to the gateway. Now, this is what the LoRaWAN network is. Now, the gateway will communicate to a core LoRaWAN setup, which will have cloud application servers. So all what LoRaWAN does is it picks up data from one point and sends it to an application. The application over there will then look at, oh, it is coming from this. So it is the house of Mr. Funseeker, and Mr. Funseeker is consuming this much power. And this is the billing I will do at the end of the month. And when you have this network set up, you have some network interfaces so that someone is monitoring if all the gateways are on. There's making sure that there's no communication issue that's happening or no congestion in the network. But it's a very, very simplistic solution that you can build on your own. The other advantage of LoRaWAN is it works in a license-free band. So in India, if you are using GSM or all those things, the telecom operators have to pay a lot of money to the government to get the license. But suppose you set up your own LoRaWAN network, say suppose in your college, in your factory, at your home, you don't have to go to the government and say that, okay, I'm setting this network, so please give me access. You can simply set up your own network. It works on a free band. In India, you have 860 megahertz plus or minus 10 megahertz band, which is free, or 2.4 gigahertz band, which is generally used by Zigbee and Bluetooth. Those bands are free. You don't have to pay any license fee. So LoRa works on that network, basically on 800 megahertz, because 2.4 gigahertz requires more power. And you can set up your own network. And typical end devices example. So class A device, suppose you have put a garbage bin sensor, which will send a signal when the bin is full, or a water level sensor to a tank. It will send the information that the water in the tank is full now. You don't require anything else to be done. So that is a class A kind of sensor. A class B kind of sensor is depending on the moisture. It will switch on the sprinkler. So what it is, a two-way communication. In a class A, it is one-way communication. Pani bhar gaya tank. Now you do whatever action you want to do. But as a sensor, I'm just reporting that the water level is so and so, and it's full now. A class B sensor, I'm reporting the moisture, that there's too much of sun, there's too much of heat. So kindly start the sprinkler. And when the sprinkler starts and the moisture comes down. So this is a two-way communication in class B. Class A is a one-way communication, and class C, if you're doing smart lighting, that means you're driving a car across a street and the lights are off. So you want a very quick response. Class B systems also are kind of low response systems because you don't have to immediately work. If you say that the moisture is gone down, even if you start the sprinkler 1 minute later, it's not going to damage the crop. But over here, if you switch on the light 1 minute later, you could end up in an accident kind of scenario. So these are the typical applications that are being used. And I'm talking of applications that have actually been used and some of the applications that we have worked on. Some of the solutions that we have built is a municipal automated meter reading network. So here, like the municipality has its own buildings. So they set up LoRa gateways on their own buildings in the locality. They didn't have to go to the government for any license fee. They don't have to go to a telecom operator to pay for their SIM card or monthly data rate fees. They simply set up their own network and they are talking to each other. There's another solar monitor network that was built, or there's a rat catcher indicator. So wherever there are warehouses, it is very essential that all the rodents that are caught are reported. And in abroad, typically in Europe and USA, you have a legal requirement that when you catch a mouse, a rat kind of a thing, you cannot let it be there to die in your mouse trap. You simply have to remove that mouse within a certain period of time. Otherwise, you are fined. So to make a mouse trap intelligent was becoming very costly, but putting a LoRa sensor over there is kind of helped reduce the cost of the system. Or college temperature monitor. This is something that some students who worked on this LoRaWAN technology in a college in Mumbai, and they have put a LoRaWAN sensor in each room so that the college can monitor if any AC has been accidentally left on, and people have, there's no one in the classroom, but still there is a cooling effect that's happening in that class. Or in some places like your server room or labs, if the temperature is going to go higher, which may damage the equipment. So that kind of monitoring they are able to do. So they have created their own LoRa network. They built their own gateway. They put in the temperature sensors and they put in the LoRa chip behind. And all of this was done by college students as a BE project, final year project. And then they have extended it and they now have a proper working solution in this college. And there are various applications. So it is being used in automation, or it is being used also in cattle tracking. So each of these cattle that you see on the left, they have a LoRa sensor in them. And if the cattle goes away or if it goes astray, they're able to find where the cattle is and track it. So I'll talk a bit of this technology. The technology also uses something called as adaptive data rate. So depending on how good or how strong the network is, it adapts itself. So over here, you can see that energy versus time on air simulation. Since the network is adaptive, it is able to communicate with devices which are as far as 14 kilometers, but with a raw data rate. So at 14 kilometers, I've shown 244 bits per second. This is the kind of simulation that we got with our systems. But if you are within 4 kilometers, you are even able to get 1 kilohertz worth of data rate. So as long as your sensors are not sending huge amount of data, you are able to work well. And the adaptive data rate, why is it helpful? Adaptive data rate is good for network. It ensures that the transmission of the end device lasts only as long as it is required. Suppose I have to send 1 kilobyte of data. If my network is good, I'll be able to send it in say 1 microsecond. If my network is bad, I may take say 4 microseconds. So since the network is adaptive, I don't have to tune it once. And most of the networks, when you set it up for a fixed data rate. Over here, the system will automatically calculate depending on the signal strength. They'll say, oh, I can transmit more data. I'll transmit and then go on low power. But if the signal strength is not good, it will say, okay, I'll keep my transmission on for some more time so that the end fellow is able to get all the data, and it does transmission at a lower data rate. This is what a LoRa does it. And a LoRa has 8 different channels with multi-data rates. So what has LoRa network done? They have made this adaptive data rate very easy. You transmit on first channel, which is 5.5 kilobytes per second, at say, which is at 869.9 megahertz. You realize that there is no acknowledgement. You switch on to say 868 megahertz, or you switch on to 867 megahertz. You select different channels, and these channels you can select every time. You don't have to latch on to that channel once for all and be stuck with that. And you keep transmitting. So you can transmit from say 240 bits per second to 5.5 kilobits per second. And this is a network that we have implemented in India. So it's not something in Mumbai. It's not something which is esoteric or something. It's very easy to implement. And as I said, that some of the sensors require a lot of security. So the LoRa network itself defines certain security. So you have two kinds of securities. You have one security from the sensor to the gateway and the network controller. So you have that red color which says this is a network session key, and you have another thing which says it is an application session key. So suppose in your college you set up a LoRa network, and one is for electrical department and the other one is for electronics department, and you have only one gateway. Your sensor with the red sensor will communicate and give you security, because all the data is coming to one gateway. You don't want the other department to know what that information is. So you have two ways of encryption. One is the encryption up to the gateway, so which ensures that no one from external agency is able to hack your system. And then once you have your own two department setup, so that you will use the black application session key. So the LoRa gateway allows you to configure 2 keys per device, and that way you can have a good amount of security in the system. So I have covered the basics of LoRaWAN, where it is being used. One of the recent applications that I am discussing with one of the suppliers, so they are building this metro network, and metro network people are actually kind of renting machines. So the man who gives those machines on rent, he says, I want to make sure that they are not using it beyond a certain temperature. So when you use these drillers and diggers and all those things, they are supposed to be working below 40 degrees. But if the ambient temperature outside is 35, 37 degrees, and when you use the machine for some longer time, it goes above 40, 41, 42 degrees. Now, since this machine has been rented by these people, the workers don't bother. They want to finish the job. But the man who has given those machines, he says, they will damage my machine by using it in higher temperature. So do you have a solution? And there I have suggested in LoRa, I said, you will put a LoRa chip on with a temperature sensor on each of your machine. So you will know whether the workers are using it beyond the rated temperature that it should be used. So as electronics engineers, what we can do? We can develop new devices and applications. We can develop different kind of sensor networks, or you can connect existing devices to LoRa, say like your water meter, your electricity meter, or you can build some campus network solutions, or you can build training kits. So anyone who is interested, you can build so many these kind of things. What is in it for computer engineers? So people who are now, say, software engineers, and they say LoRa is generating a whole lot of data and information. So you can create various kinds of database implementations, SQL, NoSQL, because you will be connecting millions of devices to your network. So you require different ways of handling the data which is coming in. Or you can create some network prioritization, which says that, okay, if the data is coming from this sensor, it will take priority over other because you are using simple one gateway. If many devices are communicating with it, it will buffer the information and then send it forward. So you can prioritize the network, and you can build a host lot of applications. Artificial intelligence, machine learning is coming up, and they require a huge amount of data. So thank you. I have covered why LoRaWAN is required, how it will help your sensors increase its life, reduce the power consumption, build a green and sustainable ecosystem, and also reduce the cost of implementation, the cost of management. You don't have to configure Wi-Fi network if the password changes. So if the cellular transmission disconnects, then for reconnection, you may have to do some manual intervention. Nothing of that is required. So you can build a nice standalone network, which is sustainable, which is with environment friendly, green, low power, and non-interfering, and you don't have to pay license fees also to set it up. Thank you. I have kind of covered what I wanted to say, and I can take a one odd question before we hand over to next speaker. Thank you.
Thank you, sir. Is there any question from the student? I think there are no questions. So thank you, sir. On behalf of VPM's Polytechnic, I would like to thank you for your wonderful presentation. Am I audible?
Yes, yes, you are audible. I can hear you.
Yes. Now, sir, am I audible?
Yes, yes.
Okay. Sir, I think there are no questions from the
Hello?
students, and
Hello.
yeah.
There is one question. I just want to know about the automated metering solutions, which has been what electronics engineers can do. In that slide, there was one automated metering solutions. So a brief idea, if
Yeah, so what we have done is, yeah. So one of the municipality wanted a solution to be built for their gas metering and water metering. So the existing water meter, you have sensors that are basically tracking the flow.
Mhm.
So what we have helped them is to put in this flow sensor
Mhm.
and connect it with a LoRa chip at the back end that works on a battery. And since LoRa is using 800 megahertz, it can communicate even if the sensor is kind of underground to a certain level. So if it is fitted on a pipe, that it is radio telephony, so it is able to communicate outside. And that way, the sensor simply sends the pressure, water pressure readings or the flow readings back to the gateway. And then the gateway sends the information to wherever you want. And then people have built their own applications on that. So all you have to do is buy a LoRa interface chip, interface your flow sensor to that. And once you have calibrated that, you connect it to your own gateway and then set it up.
okay, sir. Thank you.
Pooja, there are a few questions in the chat box. You can read that for the speaker. Just check the chat box. There are 2 questions from students.
Sir, actually, the last question, okay, why is no licensing required for LoRaWAN? I think sir has just answered.
Yeah, so there are certain free frequencies that have been given by governments all across the world. So all of us are aware of Bluetooth. So Bluetooth works on 2.4 gigahertz. If you set up your own Bluetooth network in your home or in your college, or your Bluetooth network with someone else, or Zigbee network, Zigbee has a range of say 100 meters. So these are free frequency bands which government has allotted, and all the countries in the world have free frequency bands. Some of them have allotted 400, 800 and 2.4 gigahertz. In India, you have 860 and 2.4 gigahertz, plus or minus 10 megahertz around that. So if you build your own network on that frequency band, you don't require permission from anyone to set it. So if you say create a network from Mumbai to Thane on 2.4 gigahertz with your own devices, you don't have to take anyone's permission, or 800 megahertz, 860 megahertz. So that's the advantage. You can use the LoRa chips are basically configured for either 400 megahertz or 800 megahertz networks. So in India, you can use these 800 megahertz chips and freely set up your network. No license is required.
Okay. Thank you, sir. Any more questions? Thank you so much, Abhay sir. On behalf of PPM's Polytechnic, I would like to thank you for this wonderful session. Sir, we will take one photograph with all. So I would like to request all of you to just switch on your cameras so that we will take a photograph. Students are also requested to on their videos.
Pooja madam, I think.
I request.
Yeah, Naxer is there. Okay, Naxer is there. I thought. Okay.
So all the students just start your camera so we can take a screenshot. Just give me 2 minutes. I'll take the
Yeah.
screenshot of all the pages. Thank you so much. Thank you so much.
Thank you.
Mansigar sir. Thank you.
Thank you. So shall I leave now?
Yes, sir.
Yes.
Yes.
Okay. Thank you. Thanks a lot. Thanks for giving me this opportunity to share my experience, and all the best for your future sessions. Thank you.
Thank you. Thank you very much.
Now I request Mr. Sunil Nagre sir, lecturer in Industrial Electronics Department, to introduce our next speaker. Sir.
Am I audible?
Yes.
Yeah. Good morning. Our next speaker is Dr. Ashwini Kutrashetty. She is the head of department in the Department of Electronics and Telecommunication at the Don Bosco Institute of Technology, which is located in Mumbai. Madam did a PhD from Assam Don Bosco University. She did her master's in engineering from Mumbai University. She is an educator from last 24 years with a research interest in a metastructure antennas and microsystem design. She also offers the consultancy services to companies on antenna designing, testing, and microsystem design. She is a guarantee of the prestigious IEEE Event and Activity Committee project for the year 2017. And she was a co-guarantee of IEEE HSE Event 2018, and also the guarantee of IEEE MTT SIGST Joint Funding 2019. She is a senior IEEE member holding the position of a chair at IEEE Bombay Section MTTS chapter, and she was an ex-CACOM member. She is a reviewer of IEEE Journal of Research and international conferences such as the Asia Pacific Micro Conference, and she did several publications in international conferences and the referred journals to her credit. So I welcome Dr. Ashwini Kutrashetty. Madam, you can start your session. Thank you so much.
Thank you. Thank you very much. First of all, I would like to thank Professor Moite Patil for this wonderful opportunity, and good morning to everyone present over here. Can I share my screen?
Yes, ma'am.
Madam, before I start, I would like to just check because I have 1 or 2 videos. So can I just check once if my this is shared, my computer audio is shared?
Okay.
Yeah. Can you please confirm if you could hear the audio?
Now it's not audible, ma'am.
Okay, so yeah, this is what I wanted to check. Please give me a second. I'm sorry, is it audible
Yes,
now?
yes, yes, yes. It's
Okay.
audible.
Yes.
Okay.
Thank you. So a very warm welcome to everybody and a good morning to everyone. So I've got this opportunity to present to you all on radar sensors. And this is a topic which, very close to my work, and I have been working in this domain of RF and microwaves for several years now. And, so I hope I can add some value to your understanding. So basically, I would like to, I understand the audience here is all students from diploma background who are into diploma course. And I would like to understand wherever you think you need a little more of depth of understanding, you can always stop me and ask me to explain it further. So because this is a concept which is basically a topic which is basically based on fundamentals of microwave engineering, but the underlying concept is an extremely simple concept. It is it's when you listen to the concept, you will understand that even I could have thought about it. It's that simple concept. Okay, so now basically what I'm going to cover in, today is what are radar sensors and what is the underlying basic concept behind radar sensors, and how is this concept, a simple concept, applied in various walks of life. If those of you who have heard of sensors, there is a very common myth among people that it's only used in the defense sector. But if you look around and as we see through, you will realize that we use radars almost everywhere around us. Okay, and that's the beauty as to how a simple concept can be transformed into a technology which which has contributed over years in improving the human life. Okay, so that is what I'm going to present today. And in the end, I will also show us how students can implement simple radar projects and what is the scope for them by going through this kind of a course, and also developing an expertise or masters in radars. What is the scope, career scope that you can have? Okay. So moving forward, I'm now, I just want to start with something very, very simple. All of us have at some point of time been on a hillock or on a mountain, right? So what happens when you actually scream or from a mountain top? Anybody from the audience would like to answer this? Anyone? What do you think happens when you scream from a mountain top? You know, I've given you the scenario also.
We get a broad view of entire universe.
Yes, but when you scream, what happens to the sound? Suppose you say hello. What do you get? What you hear when you?
Sometimes,
Yes, yes.
sometimes echo if it is a
Correct.
to
Yes,
point.
perfectly right. Perfectly right. So when you scream from the top of a mountain, okay, where I've shown a scenario where you have, you know, also several other mountains or hillocks around. So you will hear, if you have screamed your name, you will hear your name back, but with a delay. So that's an echo effect. So radar is based on this very, very simple concept of reflection of signals. Okay. Now, when I talk of echo, basically, when we say echo, it is always in the audio spectrum. So, which is what we can hear and we talk in the audio range, right? But radar normally works at higher frequencies, say from 0.3 gigahertz to 300 gigahertz, or maybe today currently we have radars working in 1000 gigahertz as well. Okay, so the frequency shift is the only change in the concept. Otherwise, it is the same. So instead of audio signal, you're transmitting a signal of a higher frequency, and this frequency comes back to you after a delay. Okay, so let's see how this actually happens. Basically, as I said, radar is known to be working for defense systems. Now, why do we say defense systems? That is because the whole concept of radar started in the late 1800s and early 1900s, when there was a lot of research that was going on radar technology. That's when radar was born. It was basically devised by Hertz. All of us have heard about Hertz. So Hertz was a very famous scientist who came up with this concept, but his concept was worked upon in detail by a German scientist named as Christian Holzmeier. Now, both of them started working with this concept, and basically their intention was to contribute to military system, defense systems. That's how radar is associated with defense all the while, right? Because the birth of radar was, and the objective of its birth was only to meet the defense criteria. Eventually, over the years, radar technology has found its applications in innumerable um, uh, applications. Okay, so that's how radar was born. So what happens in radar? Radar is basically an electromagnetic system, okay, what we say as EM system, for detection and locating of objects. Now, how do I do that? Suppose I have here, what you see is a vehicle, and this vehicle has a transmitter within itself. Okay, and you see here, you also see that there is a there is a antenna here. This is the dish antenna. It's a reflector antenna. Basically, this is the reflector, and what you see here at this point is the antenna. So the antenna throws the signal on this reflector, and this reflector will transmit the signal towards the target. Now, let's say that there is a target, and this target is an aircraft. Okay, so I'm continuously sending the signals. Okay, I'm not waiting that the aircraft comes and then I will send the signals. So continuously the signals are being, electromagnetic signals are being transmitted into the airspace, and let's say you have a target here, that is an aircraft. So my transmitted signal that you have thrown out in air intercepts. That means it comes across this target. Okay. Now, once it intercepts this target is a metal body. Aircraft is a metal body. So this target will reflect the signal. Metal hai, so you will get the electromagnetic waves reflected. So it reflects back. So this reflection is in fact in all directions. ऐसा जरूरी नहीं है that it will be only in the direction of the antenna. When I transmit the signal, the intercepting object can scatter the signal in all directions. But some of this signal will definitely come back in the direction of the transmitted signal. So that's how I receive it. So when we receive it, you capture the signal, and this captured signal is processed by the receiver, and it is seen on a display, which is normally a computer or different scopes that are there in the radar system. Okay, so let me go a little into details of this. Now let's say I have the target as it is. I have a transmitter. The transmitter is a high power transmitter. Normally these are magnetrons. Okay, magnetrons are high power oscillators, and they generate high power, high frequency signals. Now this transmitter, which also consists of not just the magnetron oscillator, but also a modulator. So the modulated signal that is coming out of this transmitter is given into a duplexer. Now, what is this duplexer? Duplexer is basically a switch, okay? And this duplexer has to manage the signal from the transmitter to the antenna, okay? From the transmitter to the antenna, and also from the antenna towards the receiver. It is like a switch, like how you have your SPDT switches. Okay, so the transmitted signal goes on to a duplexer. When it is putting its signal onto the duplexer, in the transmitting mode, the duplexer connects the transmitter to the antenna. Now this antenna will further transmit the signal into the airspace. Now, once it is thrown into the airspace, it is intercepted by my target. Okay, this target now reflects the signal the way I have explained a little while ago. So the intercepted signal is scattered in all directions, and part of it is received back by the receiving antenna, by the same antenna. Okay, so there's a single antenna which is transmitting and also receiving. Once it receives, now this received signal has to be processed. That means it has to be directed towards the receiver. So now the received signal is sent into a duplexer. This duplexer is now, the switch has now connected it to the receiver, and the processing takes place, signal processing takes place within the receiver. The signal processing is such that there is a threshold level that is fixed at the receiver. Why do I need this threshold level? If I don't have a threshold level, whatever I receive, okay, whatever small minimum detectable power that I receive at the receiver will be declared as the target at the by the operator. Now see, this receiver basically is, after the processing, it gives its signal onto a monitor, a computer monitor, which is today basically a computer monitor. And whereas in the aircrafts and in the ships, you have PPI. Okay, that is PPI is plan position indicator. Okay, earlier we used to have A scope and B scope and so on and so forth, which were basically CRT tubes, display tubes. But today, maybe in all your systems like aircrafts or your navigation systems, or you have your ships, there you have the PPI, plan position indicator. Or if it is at an ATS, that means your aircraft terminal systems, where you are actually monitoring aircrafts, they have huge computers. Okay, so now I'll come to the point where I said that if the threshold is not there, any minimum signal power level that I detect, I will declare it as a target. Okay, now I cannot be doing that, because instead of an aircraft, it can be just a huge bird or a bird, which is also reflecting, right? So there is a threshold level that is set, which helps us decide whether the target is something that we should be concerned about. Is whether it's an aircraft or it is, some other today we have a lot of drones flying around. So whether it's a drone or something else. So this is the basic concept of how a radar works. Now, today, this technology has advanced so much that I just do not have simply an indication whether the target is present or not. Okay. Now, of course, by using a radar, I can not just tell, not only tell that there is a target, but I can also tell whether the target is coming towards me or moving towards, moving away from me, if I am the source. And not just that, we can find the velocity, you can predict the range, how far is the target from the base station, and whether it is receding or it is advancing from the base station, with what speed is it arriving towards us. All of this can be predicted, and also today I can categorically detect as to whether the target is an aircraft. How big is the aircraft? Is it a small aircraft? It is a huge aircraft. All of this can be done by the high-end signal processing capabilities that our systems have today. Earlier, it simply worked on a basic concept called as radar cross-section. A radar cross-section kind of gave a rough idea as to what is the object. Okay, but today we can actually create an image on our system display. So that's the advancements of technology. So while I have discussed all of this with you, it's important for us to go a little more and understand about, how exactly is the duplexer controlled. Now, within these modulated signals that are transmitted by the transmitter are mostly pulses. Okay, they are high power pulses. That means during this short duration, where you see the on time of the pulse, within the short duration of the pulse, high power is transmitted. Okay, and for the next duration, next duration that I have listed here as listening time, during this time, there is no transmission of signal. So transmission of signal takes place in small, short bursts of pulses. Okay, so this pulse, during the pulse duration, okay, so the duration is divided into two phases. One is the on time of the pulse is the transmit period. Okay, and in the off time of the pulse is the listening time. Okay, during the transmitting time, the duplexer is connected to the transmitter. The transmitted signal is put onto the antenna through the duplexer. Okay, once it intercepts the signal, the reflected signal is now listened, or it is captured in the listening time. For the duration that I am in the listening mode, your radar is in the listening mode, you will keep on receiving the reflected signals from the interception. Okay. Now, during this listening period, all of the signal processing takes place, and again it switches back to the transmitting mode. Okay. Now, how do I actually calculate? This is the basic working. Okay, for if I have a single antenna which is transmitting and also receiving, this is the basic operation. Now, when all of this is happening, how do I know, first of all, that there is an antenna, that there is a object? I have just explained to you. How do I know? There is a received signal, the reflected power is so high that I declare that there is a target. But just knowing that there is a target is not sufficient. I have to tell as to what is the distance between the base station, that is the transmitting station, and the target. So for this, we use a very simple concept. Okay. Now, the range of this target can be determined by what we know as the the transmit time. Transmit time, TR, that is the duration for which the pulse is on. Okay. Now it takes the radar signal to travel to the target, some time to travel to the target and back to the the antenna, right? So that means now with what speed is the signal that you have transmitted traveling? It is basically an electromagnetic signal. So it will travel with speed of light, that is 3 into 10 raised to 8 meters per second. So you have to multiply the range. It is the two-way range from the transmitter to the target and back from the target to the transmitter, right? So 2 times of this path R that you see in the figure here, the radar range, 2 times of the range divided by the speed of light. Okay, so that is actually the formula to calculate the transmit time. So when I just reverse the equation, I'll have the range to be equal to the electromagnetic speed, that is speed of light, into the transmit time divided by 2, okay, because of the two-way path, right? So this is a very simple formula which will give me the range. Okay. Now, I'm not going to get into too much of mathematics. Though the whole of radar concept is dependent on what we know as radar equation, but I'm not going to go into that. You can read about it on any portal you can Google about it, radar equation. But it's a very important concept, yes. But I think our discussion can go ahead without getting into the mathematics of it. Fine. So now we know how the radar is detecting, and also it is ranging, that is finding out the range. That's how radar gets its name. Radio detection and ranging. Okay, part of radio is RA, D of detection and ranging. So that is radar. Okay, so now we have seen as to how a target can be detected, and that's basic on this reflected signal concept, that echo concept. But how do I find its velocity? Okay, how do I find whether it is coming towards the transmitter or the target is moving away from the transmitter? Now, the target is not a stationary target, isn't it? It is always moving. Okay, so moving target will move towards the transmitter or the base station and will also move away from the base station. So how do I calculate the speed with which it is arriving and so on and so forth? So in order to know that, this is basically based on a very simple concept called as Doppler shift. You must have read about it, you must have experienced it, but never actually, when you have experienced, I don't know how many of you have really related to a concept or a technology. Okay, so let us see how that happens. Now, Doppler shift. What do we mean by Doppler shift? Suppose I have, this is the position here. The receiver is at rest. You see the person's photograph there. Okay. Now, when the receiver is at rest. Okay. Now, let's say there is a vehicle that is coming. That vehicle currently is also in stationary position. So you see that any kind of transmission or reception between the receiver and this vehicle is actually, it's constant. Fine. Okay. Now, let's say now the vehicle has started moving towards the receiver. Okay. Now, let's see what happens. First, let me take you through the, just a second, please. And the third word is at 160. Okay, what is that we have observed here? We have observed that while the ambulance was approaching the listener, okay, it was very loud, right? It was very, very loud. So the frequency is very high. And as it moves away, okay, the pitch recedes. Okay, so that is when we say that the frequency starts reducing. So if there is an object moving towards the transmitter, the frequency of the reflected signal goes on increasing. As it moves away from the transmitter or the receiver, the reflected signals start reducing in their frequency. Okay, the signal reception goes on reducing. So that is called as Doppler shift. And this Doppler shift is used as a basic concept in calculating the velocity of an object in case of radar technology. Okay, I hope you have understood this. So the difference in the time, okay, the time difference that I get as the object moves towards and away gives me whether, so you see that as the object is moving towards me, the time difference goes on reducing, and as it moves away, the time difference goes on increasing. Okay, so that's how we estimate and predict the velocity of the object and also predict whether it is moving towards or away from the transmitter. Fine. So all of this is working at some electromagnetic frequency. Like I mentioned, it works from the UHF band to the EHF band, and also from 0.3 gigahertz to, here the scale shows 100 gigahertz, but there are a lot of space applications, or what they call as remote sensing applications, which work at much, much higher frequencies. Okay, and so let us now go ahead and see. Here what you see on your screens are some of the applications which are mentioned, but there are many more aspects to these applications which I will be discussing very soon. Before we go to the applications, I would like you to appreciate another form of this technology. Monostatic radars, there are three, basically they come in three forms, or you can call them as types if you would like to. Monostatic radars, bistatic, and multistatic radars. Now, what are monostatic radars? Monostatic radars are the case where you have a single antenna which will also transmit and receive. यानी transmit भी वही करेगा और listening mode में भी वही antenna रहेगा. Okay, and bistatic radars. Now, most of the defense antennas, okay, which I showed you, a vehicle with with a radar, most of the times they are monostatic radars, because in the war front you need to have a system which is capable of doing both the things, because you may have several restrictions. You may have restrictions of space, the kind of terrain that you are, and so on and so forth. So monostatic radars are basically defense oriented, and of course there are there are ship navigation, that is the marine applications, which also use monostatic radars. Bistatic radars are radars which have two different a different transmitter and a receiver. That means the antenna that transmits is different and the antenna that receives is different. That means there is a transmitter station which is a little away from the receiver station. Okay, so that's how you have a bistatic radar. And multistatic radar. Multistatic radar is an excellent advancement in technology, where a single where you see here you have three antennas. Okay, and this is an example with three antennas or three stations, where you see that a single antenna is transmitting and also receiving, the blue curve here. Okay, and you also see that at the same time the radar has the capability of behaving like a bistatic radar, so it can transmit and the other one receives. You can see the yellow one, or it can, or the light blue arrow, you see that one is transmitting and the third one is receiving. So all of this, that means a single station can work as monostatic, bistatic, and also bistatic and multiple bistatics, not just one station. It can interact with multiple other stations. So that is called as multistatic radars. Today we are in a technology domain where we are talking of MIMO systems, whether it is your handsets or it is radars or your 5G communication systems or several other communication systems are all penetrating into what is called as MIMO systems, that is multiple input, multiple output systems. Okay, so multistatic radars support MIMO systems. Fine. So once we have got this, now let's go and see as to what are the common applications that we can deal with in radars. Okay, first of all, you have air traffic control, which is a very common thing, and along with defense, a lot of air traffic controlling was also implemented way back in the World War itself. Okay, so air trafficking basically can be for defense, for commercial purposes, where you have your ATS. If you are, whenever you go towards the airport, you see that there's a huge dome there where there are people who also have a eye visibility, and also they have better reception of signals from all the sides. So you see that dome is here. You can see it on your screens as well. Okay, so here for air traffic, you have a lot of radars implemented where the traffic can be controlled. Also, under air traffic comes systems which are on board on the aircraft. Now, aircraft, when it is actually landing on the runway, okay, now the pilot doesn't have a camera view of the runway. We all understand that, right? So how is he actually managing to land exactly on the center line of the runway? The runway has a thick line that is painted all through at the center of the road, right? What we call as the runway. Now, how is that managed by the pilot? That is because he has a navigation system which is called as instrument landing systems on his board, okay, on the aircraft in the cockpit. So there, the radar is actually, they are accurate radars which are constantly transmitting signals, and they gauge the height of the antenna, height of the aircraft with respect to the runway as well. Okay, and that helps the pilot navigate and land on the center line of the runway. So that's, instrumentation landing systems. You have marine radars which can guide the ships, avoid icebergs and several other things. Because see, when you are in an ocean, you cannot get down and see what is there below, right? So continuously there are reflected signals that are received by the ship. Of course, you have to transmit, and then the ship gets the navigation as to whether there's an object below or whether he has to turn the ship, and so on and so forth. Then you have space radars. Space radars are radars which actually track your satellites. Okay, not just the satellites, but also all of us understand with advancements in technology, we have not only created debris here on Earth, but also we have created a lot of garbage in space, right? That is called as space debris. Now, all the satellites that disintegrate over time, once their lifetime is over, they are all floating there on your, in space. Now, when I launch a new satellite, I want that my satellite should be safe. It shouldn't go and hit on to a debris, and the debris, kills my solar panels, and then eventually the satellite that you have launched collapses, right? Because it has to be powered. So if that has to be taken care of, then the satellite also has to have within itself a system that keeps telling it, look, there's an object that is going to come in and hit you in so much time and in so and so range. So you have to turn over, you have to maneuver yourself. Okay, so there's no human being there who's sitting with us with a system, but it is all done remotely. Okay, so remote sensing is a very, very advanced technology which uses radar sensors to sense debris or any other satellites, to avoid collisions between satellites, the debris, and so on and so forth. So, and of course, a lot of applications to remote sense as to see, to have geographical studies of Earth, Moon, while landing systems on the Moon or different planets. For all of those, radars are used there. There are a lot of radars which are used as weather radars. When the prediction of rain, okay, prediction of snowfall, what is going to be the intensity of all of the snowfall, intensity of fog, okay, precipitation, all of this is done by weather radars. Okay, so that's again, they are basically pulse Doppler radars. Pulse Doppler radars are nothing but transmitting modulated pulse signals, which are which they are called pulse Doppler because modulated signals, pulse signals are transmitted, and there is a Doppler effect also which is studied. So that's why we call them as pulse Doppler radars. And these pulse Doppler radars help us find the intensity of precipitation. The data can be analyzed over regions and over different durations of time. Okay, without actually stepping out of your office. If you have a weather station, you can monitor anywhere around the world. If you can connect yourself to satellites today, you can, through weather satellites, you can monitor, observe, predict, and also evade a lot of natural disasters. Another interesting application is the radar gun. Okay, now this radar gun is a very interesting concept. And so I'll just, as young students, this radar gun, I'll just show you, run a video for you all. So the basic common application of radar gun initially was to test the, the velocity of vehicles. Okay, what is the velocity of vehicles? That's why you see, if you go on Mumbai-Pune Express Highway, you will not see any policemen, but then you are caught or you are charged for speeding. There's a speed limit. For small vehicles, it's 80 kilometers per hour. For heavy vehicles, it is, it's 180 and something like that, right? So if you speed beyond the limit, you will be fined for it, right? But then there's no policeman. How does that happen? Because there is a vehicle, police vehicle, who has a radar gun, and the speed gun helps him see if he is just showing the speed gun around towards the moving vehicles, he can estimate it. He actually gets the actual reading on his speed gun. So I'll show you that video very soon. Before that, since we are talking of so many applications, and also I have hit upon defense, I would like to tell you that if there is a technology that can detect a target, okay, suppose there is an enemy aircraft, I can detect it. There is also a technology which can help me save myself from my enemy radar. Okay, now how do I do that? Okay, so there is, in earlier days, in World War II, the pilots used to throw a lot of metal shafts. Now, shafts are small aluminum sheets, okay? Aluminum sheets, waste sheets of certain dimensions. The pilots used to throw them in order to create clutter for the radar. Now, what happens if I have a lot of these metal pieces falling from the air? The radar will actually pick up all the reflected signals. But all of that comes onto the receiver, and it's huge amount of noise. And in that noise, okay, this system is not able to recognize that it is actually an aircraft, because the RCS, that is radar cross section of the object, doesn't look like an aircraft, but it looks like something else, a huge clutter. So then you can simply get away with it. That's how you fool the radar. Now that was the earlier method. Now systems have become clever. So shaft will not work anymore. After the World War, people came out with electronic interference. Okay, electronic interference is nothing but creating countermeasures where the aircraft is actually throwing itself. It is throwing lot of signals, okay, noise signals when it comes in the vicinity of the enemy radar. So when it throws so much of noise signals, the enemy radar kind of gets jammed. It's a concept of jamming, okay, electromagnetic jamming. So this is called as creating false electronic interference so as to dissuade your radar, okay. So that's how you can save yourself. The third one is called as the stealth technology, and that is the most recent technology. Of course, it's already around, I think, 2 to 3 decades old. So what happens in this stealth technology? In stealth technology, the aircraft is invisible to the radar. Okay, the radar just cannot see it. How? Why? Okay, now if you look at the images here, you will see that if you look at the third one, the third image is a normal aircraft. Okay, it's a normal defense aircraft without stealth technology. Look at the corners, the amount of corners that this aircraft has. Okay, not just the nose, of course, you also need to maintain aerodynamics, but it has those wings, and on the wings there are some things, some protruding objects. You can see the tail. Again, there's a protrusion there. All of this, right? But look at the first two images. The first two images have rounded corners. Though you cannot avoid corners because you have to maintain aerodynamics of the aircraft. So you cannot actually have all rounded. But then look at the how the design has transformed. There are no extending tails. Okay, the top. I mean, if you can call it a tail, and also look at the nose, how it is shaped. It has softer corners. When you have softer corners, in your design, the reflections from your aircraft or from the object are much lesser. The highest reflections that the radar receives is from a corner, right angle corner. Okay, whereas the least is when it is a sphere. So the radar cross section received at the receiver is least for a sphere and highest for a right angle corner. Okay, so if you avoid corners and make them as spherical as possible, then you are reducing the reflections. This is as far as the design of the aircraft is concerned. Whereas now I can also paint it with material that can actually absorb the electromagnetic signals. Okay, so when I do that, the reflected signal back to the radar is minimalistic and which gets lost in the noise that the radar receives from the airspace. Okay, so that's how I can dissuade my detection. Okay, so that's a very important, also an interesting concept called as stealth technology. A lot of people are working on stealth technology today with different nanomaterials coming in to picture. Okay, now I want to take you to how sorry, automotive systems can also have found radar as an application. What do we mean by automotive systems? Your cars. Today, the cars, simple cars like Honda City give you a cruise mode. What is the cruise mode of travel? Where you can simply press the cruise button and just take off your legs from the, clutch gear and your brake. And if you set on an express highway kind of a situation, if you set the speed, it will just keep on traveling at the same speed. All you have to do is hold the steering and travel. Okay, so that you can save yourself from some kind of efforts. Okay, otherwise, this is what we have currently. But think of autonomous vehicles. Okay, where you are driverless. There is no driver. Okay, so that is also very much coming in. Before we go to autonomous and what the cruise mode that I discussed, Today there are vehicles like today there are vehicles, lot of Benz and BMW vehicles which use radar concepts to at least 10 radars along with lidars. Lidars are light detection and ranging, and some camera based sensors. All of this work in symbiosis to give an autonomous feel to the driver. Okay, so it will actually avoid collisions. It will tell you whether you can change the lane, whether there is a vehicle that is coming from your left side, at what speed is it coming, can you maneuver. All of this gives the driver a very good experience of driving, okay, which is called as radar based 360 degrees surround view. Okay, it gives the driver a 360-degree surround view. Okay, now with all of this coming in, okay, see what is that is there. If you have a vehicle, now this vehicle, the higher end vehicles today have long range radars that you see here. The color codes are there, long range radar. There are short range or medium range radars, and there are ultrasonic sensors as well. There are lidars, that is, instead of electromagnetic waves, it works on light. Okay, reflection of light is measured and the range is calculated, and detection also is possible. So that is lidar, and you also have high-end cameras. So all of this put together in a system, you arrive at modern advanced driver assistance systems. These are called as ADAS systems. Advanced driver assistance systems, ADAS systems. Now these ADAS systems basically, as far as the radars are concerned, work in the frequency spectrum of 24 gigahertz and 77 gigahertz. Okay, the short range radars are basically at 77 gigahertz, and also the medium range are between 24 and 77 gigahertz, and the long range are at 24 gigahertz. Now, if you are thinking carefully and listening to me, I said the short range is at the higher frequency, that is 77 gigahertz, and the longer range is at 24 gigahertz. Okay, that is because you know that distance and frequency are inversely proportional. Okay, when I say distance, it is wavelength, in terms of wavelength. Wavelength and frequency are inversely proportional, and hence, at higher, for shorter distances, I use higher frequencies. Now, with all of these put together, okay, now I will just like to show you an example of Benz E-Class 2016 model. What is the long range? It is 250 meters. The shortest range is 40 meters range, and the mid range is 80 meters range. Look at the sensors. Okay, there are different positions on the vehicle where you have these sensors implanted, and they continuously guide the driver. Okay, this is moving towards autonomous vehicles. Okay, this is, even with drivers, this is currently there, and you also know that a lot of testing has happened for autonomous vehicles, driverless travel as well. Okay, what is the concept of radar that is used here? Here, both the pulse Doppler radars are used, and continuous wave frequency modulated waves are used. That is, it is called as FMCW concept, where you have a frequency modulated signal that is transmitted, and they are continuous, they're not pulses. Okay, so the transmitter and receivers are different. So you have frequency modulated signals which are transmitted, and the interceptions are processed. Okay, now moving forward, I would like to just show you this small clipping of.
Mercedes-Benz has long believed that the best way to survive an accident is to avoid one. Rear-end collisions are one of the more common types of accident, and one that might be avoided with the help of an advanced new system called Collision Prevention Assist. Anytime you're driving over 20 miles per hour, Collision Prevention Assist is comparing your speed to vehicles or objects ahead. Using radar, it can sense when a possible collision is likely. It can also detect stationary objects when you're driving up to 45 miles per hour.
I'm
As
just
soon as the
interrupting
system
you as
detects
video
an
is not
insufficient
visible.
safety,
Oh, okay. I'm sorry.
Ma'am, video is not visible. Audio is coming, but video is not visible.
Okay, okay. Just give me a second.
Huh.
Can you see my screen, madam? Hello?
Huh?
Yes, ma'am.
Okay. Please confirm if you can see and hear as well.
Yes.
Yes, now it's visible.
Mercedes-Benz has long believed that the best way to survive an accident is to avoid one. Rear-end collisions are one of the more common types of accident, and one that might be avoided with the help of an advanced new system called Collision Prevention Assist. Anytime you're driving over 20 miles per hour, Collision Prevention Assist is comparing your speed to vehicles or objects ahead. Using radar, it can sense when a possible collision is likely. It can also detect stationary objects when you're driving up to 45 miles per hour. As soon as the system detects an insufficient safety buffer, a visual warning illuminates. If the distance is decreasing rapidly enough, a warning chime sounds. This alerts the driver to initiate braking. As soon as you step on the brakes, the system's adaptive brake assist precisely applies the optimum braking force automatically. Should the vehicle ahead brake harder or start to pull away, the brake force is instantly adjusted. By braking only as much as necessary to avoid the collision and activating the brake lamps, drivers behind you also have more time to react. And if it appears you cannot avoid the collision, the system engages the features of pre-safe to help prepare the occupants. With Collision Prevention Assist, Mercedes-Benz once again shows that the future of driving safety is often right in front of you.
Okay, so in no way I'm promoting any product. It was just, from an educational point of view. Okay, so this was about driving safety, for which we use radar systems. I'll request the organizers, please let me know if I'm going overboard with time, because I have not noted when I started this. Okay, the second application that the other application that I would like to highlight is something that each one of us as Indians has to be very, very proud about it. And those are giant meter wave radio telescopes that you see on your screen on the right side. Okay, now these giant meter wave radio telescopes, it is called as GMRT in short form. Okay, now what are these telescopes for?
Ma'am, just a request. Can you
Yes,
please conclude in next 5 minutes?
Yes.
Okay.
Sure. Yes.
Thank you.
Thank you. So you have these, it is NCRA, if you know what is NCRA, it's National Center for Radio Astronomy, has set up a unique facility for astronomical studies. Okay, now this is one of its kind in the world, and it is indigenously designed and installed by TIFR. There are 30 fully steerable gigantic parabolic dishes. What you see, these are called as parabolic dishes, and each dish is of 45-meter diameter. Okay, they are huge ones, and you can visit this place. It is in Pune. It is in a place called as Narayangaon. Okay, and all these antennas operate at 50 megahertz and 1500 megahertz. Now, these are low frequencies. What do? They transmit the electromagnetic waves towards the atmosphere in space. Okay, and they receive signals. Now, like I said, these are for astronomical research. So a lot of scientists from worldwide come over here to collect the data of different celestial bodies or stars to study about different concepts of astrophysics. So this is again based on the concept of radars. Now, another very important application is avalanche radar. In places like India, tropical regions like India, we don't face this problem. But in European countries and in American countries, where there is huge snowfall on mountains, there is always what is called as avalanche. Avalanche is a speeding movement of snow, okay, snow masses. And as you know, wherever there are mountains and valleys, there is human habitat. So if the human habitat does not move out in time, then all of that snow will cover the valleys where there is, a lot of civilization. So that is why they have what are called as avalanche radars. Okay, I will just take you through this video.
Yes, yes, ma'am, it is audible.
Lack of time, I'm cutting it short. Okay. The next very important application are called as ground penetrating radars. Ground penetrating radars are techniques are used in applications where I don't want to break out things and I want to detect it first. Okay, for example, if there is an archaeological valued place, okay, for example, you have probably gone to Vijayanagar Empire, Hampi, which is in Karnataka. Okay, so if you go there, a lot of archaeological survey keeps on going on. So they don't dig all the time with no ऐसी सब जगह dig नहीं करते. They go with GPRs, and you see that this GPR will now transmit electromagnetic waves and it will detect if there is a buried object. Likewise, it is used in forensic science. It is used for detection of cracks in concrete structures, to measure the thickness of bridges, roads, and so on and so forth. A few years ago, there was caving of roads in Mumbai. Okay, that is when VJTI was given the work of going with a GPR and making a test to analyze as to what is the amount of caving inside. Caving in the sense, road mein khadda ho jata hai and all of that road just collapses inside. So this happened somewhere in, if I'm not wrong, Parel or Dadar. And so this contract was given to VJTI professors who went there and did this kind of analysis for BMC. Also for pipeline maintenance, okay, to measure if there is any cracks in the pipeline, underground pipelines, to see whether, you know, in case of agriculture, whether the nutrition level of the soil is intact. For that also we use GPRs, and to test the amount of pesticide content within the soil. GPRs are very much used. Now, some very indigenous radars that are designed by our own scientists in India. Now, NARL is again a research laboratory which is called as National Atmospheric Research Laboratory. They have set up an MST radar. You know, in the atmosphere, there are different layers like mesosphere, stratosphere, ionosphere, troposphere, and so on and so forth. So to conduct atmospheric research, this MST radar is set up in a place called as Gadanki near Tirupati. Okay, these operate at 53 megahertz, and it is an array of 1024 Yagi antennas. You can see the spread, and it is in a valley between mountains. Okay, and it is designed to study winds, waves, and turbulence, that occurs in the atmosphere, plasma irregularities, and also the different electrodynamics in the ionosphere. Okay, So moving forward, I have another one which is indigenously developed by our Indian scientists. It is called a stratosphere-troposphere radar, which is actually deployed in the IIT Guwahati University. Sorry, not IIT Guwahati. It's Guwahati University campus, and this operates at 200 megahertz, and it consists of again an array. An array is nothing but multiple amounts of similar antennas, which is 576 antenna elements that are laid. You can see here in the picture. This is used for forecasting of atmospheric parameters in the northeast region. Okay, so moving forward again, a very interesting concept. What I want to try to show you is that radar can be used in all walks of life. And this is a very interesting radar called as harmonic radar. Now, these harmonic radar is used by ecologists as a way to track insects. We very well understand that because of climate change, our climate is deteriorating, and the best indicator are honeybees. Honeybees, if their population, they say that if the population of honeybee dies down, that day it's end of humanity. Okay, so it's very important for us to conserve and preserve our insects as well. So harmonic radars are a way that are used by the ecologists to study the health and track the honeybees. What is done is on the honeybee, okay, a small diode is implanted, and on that diode has a small string that you see here, which is behaves like an antenna. Okay, this actually is 3 milligram weighing antenna, which is sticked on to the, it's a biologically safe glue is used to stick on to the body of honeybees, and then they are set free. Then the ecologists actually use a radar gun, a harmonic radar gun, which will actually transmit the signal. This diode will generate a harmonic frequency of the transmitted signal, and it transmits it, and that is received back by the gun. Okay, this way the honeybees or any other insects are kept track of, their movements are tracked, and their complete study of the insects, their behaviors are all.
Sorry to interrupt, ma'am. Can
Yeah.
you please conclude, as the next speaker is also waiting?
Yes, sure. Okay, so this is about harmonic radar. Madam, if you don't mind, give me 1 minute so that I can just talk about radar project prospects for students. So
Okay.
students can work on mini projects based on ISM bands. When I say ISM, it means industrial, scientific and medical band. These are unlicensed bands. You don't have to take anybody's permission, like how Mr. Abhay Fansikar, our previous speaker, just mentioned. So there are open source projects which are on the MIT, that is Massachusetts Institute of Technology websites. You can refer to that. There are development boards that are available. They are not expensive. They are, your small college can actually sponsor them. While Texas Instruments has development boards which the student can actually use. Simple embedded programming will be there, and they can make their own radars. Also, there are highly sensitive radar proximity sensors which are available, and they are inexpensive, low cost, which can be used, and all proximity sensor projects can be actually implemented by using these kind of high sensitivity sensors. This is regarding your projects. As far as the career prospects goes, you can get yourself enrolled in defense forces, and you can work on radar systems in the non-combat role. Engineers in non-combat role work on in the defense. Field service engineers or test engineers. Radar data analytics for those students who have a blend of computer programming and also electronics are very good at, can have a very good career in radar data analytics. You can also work as design engineers, because there's no radar if there's no electronics and communication. So design engineering is also a career prospect for all of you. Okay, so with that, I end my session. Thank you very much for your patient listening. I'm open for taking 1 or 2 questions if the organizers feel it's right.
Thank you so much, ma'am, for this wonderful talk. Actually, all the videos and the entire presentation was very beautiful, but actually, due to stipulated time period, we had to announce that.
No problem.
On behalf of BPM's Polytechnic, I'm grateful to you, ma'am, for sharing your wonderful knowledge with all the students, and definitely it will help all the students for their future. Thank you so much, ma'am.
Thank you very much.
Now I would like to request Mrs. Amisha, ma'am, lecturer, Industrial Electronics Department, to introduce our next speaker.
Can I leave, ma'am?
Yes, ma'am. Yes.
Okay, thanks a lot. Thank you for this opportunity. Have a nice day. Thanks.
A very good morning to one and all. It's a great pleasure for me to introduce a next speaker, Mr. Srinivas Kulkarni, sir. Sir is basically an industrial automation specialist. He's completed MSc, that is in solid state physics. Presently, sir is working in Sage Automation, Thane, as a center manager. Sir also worked in the Prolific Private Limited company as a corporate trainer and project work assistant. Sir also worked in the Abhinav Junior College as well as the KC College of Engineering as a physics lecturer and the applied physics lecturer. Next slide, please. Sir is also working on the various platforms like they handle the different types of PLCs such as Siemens, AB, Mitsubishi, Delta, different types of SCADA, HMI, industrial networking, instrumentation, pneumatics, and the sensor technology. So when I request sir to present the next, that is today's presentation topic, sensors in the process plant. Thank you, sir.
Yeah, thank you, Pooja madam, and all the faculties who are present today. All right. Let me know who are the attendants today. They are all final year diploma students or from a specific department. Pooja or someone.
The students are from electronics, electrical, and instrumentation department, and second year, third year. Even first year students have joined.
Okay. Thank you. Okay, so without losing much time, I will just start. I think I will stop my video. I'm just sharing my screen. Yeah, so good morning, all the students, as well as all the faculty members. And thanks, Pooja madam, as well as other faculties for giving this opportunity. Yeah, students, so today we are basically going to talk about sensors in the process plant, process industries, right? When we talk about the process, basically to be in a very simple language, if we have to define a process is nothing but a step-by-step execution of a particular part or a series of actions, to get a desired result. Now, this desired result can be a product, it can be a technology, it can be an intermediate part of the final product, or it can be a sub-process of a final process. To give you a few examples of the process plant, so these are some pictures of the process plant. If I start from the top left corner, there is the image for the process plant of the water treatment plant, right? So where the sewerage water or maybe the impure water, right, comes, and that is the input for this plant. And then there are various different sensors which are used, the controllers which are used, And then through this automation, you get fully processed water. So that is one basically an example of a process plant where the step-by-step execution. So from the impure water to get a pure water, there are some processes which we have to follow, right? So there comes the process industry. The lower one is a electrical power plant. Below is a pharmaceutical plant. Then you can see the oil and gas plant. That is, the picture from the ONGC at the center. Below there is a automobile plant. Then there is the food processing industries. This is ice cream factory where the ice cream cones are, packed and, they are processed. Then there is a steel manufacturing process. Then there is aluminum foil manufacturing and in the form of coil. So specifically the companies like Hindalco and all that, they are into this process. So if you see in all these images, there is one thing which is common is there is some raw material or maybe some input, which is you have to do some process on that, some step-by-step execution. If it is a water, to purify that water. If it is the oil and gas sector, you remove the crude oil from the seabed and then do some various different processes on that to get vegetable oil, a transformer oil, and various different types of oils which are used in the industries. If you go for a pharmaceutical or where the syrup from the basic chemicals, whenever you go to the medical store and buy any product, you always see that there is at the back, on the back side, there is always written that what is the type of the mixture which is used in this particular tablet or the syrup. So there are various different types of chemicals, those are processed. And then after doing that process, you get a final product. If you go for automobile sector, same thing. The car, the mudguard, the internal machine, the wheels, the glasses, everything, they are manufactured separately. So manufacturing of the glass is basically one separate company, but this glass is used in suppose a Maruti or maybe a Mercedes factory. So this is basically a sub process or maybe a sub part of the final part, right? So in that way, these are all basically the examples of the process industries. If you go for aluminum foil, you may be drinking the cold drinks or, in the soft tin or what we can say the aluminum container. So those containers are then made from these foils. So that is again, the final product is different. This is in between product. So these are all examples of the process industries. Now, friends, basically, as you are heading towards industry 4, the new technologies are emerging, and day by day the industrial field is, the automation is entering into every walks of life. It is also entering into the industry, and the picture of the industry is, changing drastically. A lot of things are controlled, in a humanless environment. In fact, what is basically the automation? In a simple way, the humanless products or humanless process, where you are removing not exactly 100%, but you are trying to remove more and more human intervention and trying to execute most of the process through automation, through machineries. Now here comes the role of the sensors, right? Sensors are playing a very, very important role in this, basically the automation process. If we talk about the today's industries, you are basically, if you can see the heading, I have written that sensors and instrumentation, basically they are called as eyes and ears of the industry. Because just like eyes and ears, they gives the signal to the brain, right? And then the brain do the processing to take the decisions, and our actuators are like hands and legs. These are like our actuators. In the same way, industry also works. There are various smart sensors used in the industries. I'm going to cover a few of them, but these sensors are basically generating the signals based on some parameters they are measuring in the plant, and then they give that signal to the controllers like PLC, PID, DCS, PC-based systems, and then finally, the decisions are taken by these controllers. So here, these sensors basically are playing a very, very important role. Now, there are various different types of sensors used in the industry depending on the application. One of the common application is basically the proximity sensors, right? The proximity sensors are used in various different types of applications. As you might be studying the proximity sensors in your syllabus, right? So what is basically a proximity? Proximity means nearness, right? So these sensors, these are the contactless sensors, and they detect the presence of a nearby objects, right? So how basically these proximity sensors are working? They are emitting some electromagnetic field or electromagnetic radiation. And whenever there is a change in that electromagnetic field or some return electromagnetic radiation is received by the sensor, accordingly, some triggering, some oscillating circuits or some triggering circuits are present inside the sensors. They trigger and the signals are generated, which are given then to the controllers. Okay, this is a simple, in a simple words, this you can say that this is a proximity sensor. Now, these proximity sensors, they come in various different forms. They are like optical sensors, inductive sensors, capacitive sensors. These are few examples of the optical sensors. Okay. One of them is a through beam proximity sensors. Okay. Through beam proximity sensor, as the name suggests, you can see the diagram on the right hand side, the top one. The transmitter is encapsulated in a different, sensor. The receiver is a different, and the in-between medium is basically the medium for detection of the object. So the transmitter is continuously sending the infrared, signals in the infrared region, which are received by the receiver. When this is basically interrupted, okay, the object is sensed and the receivers at the receiver side, the signal is generated. The retroreflective sensor, the terminology or what we can say, the arrangement is little bit different. The transmitter as well as the receiver, both are present in the same cabinet, you can say. And then there is a mirror in front of them, right? So when the transmitter transmits the signal, it is reflected back from the mirror and received on the receiver side, okay, which is again present in the same cabinet. The diffuse proximity sensor is something different, where the object itself is acting as a reflector. So there is no mirror. Again, here the transmitter and receiver is present in the same cabinet, but when the transmitter transmits the signal, the object, the light gets reflected from the object. Generally, all these, what we can say, the sensors, they are sending the light in the IR region. Now, what are the applications of these optical sensors? One common application is basically detecting the object. Okay, but you may see that through beam sensor and the retroreflective sensor, you may say that the application is almost same because only the arrangement is different. The transmitter and the receiver are encapsulated in one cabinet, or they are in different cabinet. That is the only difference? No. Actually, through beam sensor can detect only the opaque objects. As you can see, so there is a can which is coming, right? And that can will be detected, right, by that through beam sensor. But through beam sensor cannot detect the transparent object. So if you are working in some water treatment plant, or if you are working in some say glass related manufacturing industries, there you have to also count or detect the transparent objects. So this through beam sensor is not applicable there. So your application, according to your application, the sensors are designed. So for that retroreflective, what is the concept there? As the concept is very basic, which you have studied in maybe 9th, 10th standard, or maybe the first year of the diploma, that whenever light travels from rarer to denser medium, it changes its path and the time required is more. So that basically changes in the signals are detected in a retroreflective sensor, which is most of the time it is also called as a reflex sensor, and then it detects the object, right? So in a transparent, if I'm working in a plant which is related with some transparent object, okay, the retroreflective sensor is more suitable as compared to through beam. I think am I clear, students? So if you have any doubts, if you have any questions, you can put in the chat box while this discussion, so that at last I will try to give the answers to them. Again, the diffuse sensor is normally used for counting the objects. Like on the right hand side top corner, you can see the image that there are ceramic tiles which are coming, and the diffuse sensor is fitted in that. Its range is almost up to 8 meter. So up to 8 meter, it can detect a particular object. So if I have to send these tiles, say a group of 10 tiles for the packaging, so the conveyor will be continued till this diffuse sensor will generate the 10 pulses. After 10 pulses, the counter will be stopped. The conveyor will be stopped. It will go for a packaging, and then the conveyor will be resumed. So like that, there are various different applications of the diffuse sensors, but most often in the industry, it is used for counting the pulses or counting the objects. Okay. The next proximity sensor is a capacitive proximity sensor. Again here, capacitive as well as inductive, which is the next sensor which I'm going to discuss. Okay, in a capacitive sensor, what it consists of? It consists of an oscillating circuit, electrodes, and a detector. As you can see in a diagram, that when material moves into this oscillating field, so first of all, that oscillating field is created. Okay, there is some specific region, right? And then when the oscillating field is disturbed, basically the simple rule of the capacitor is what? When anything in that oscillating circuit comes into existence, any object or any other person, right? What happens that the capacitance between the two plates, that magnitude increases, and that is accordingly some switching signal is triggered inside, and which detects the particular object. So this type of application you can see very commonly in malls, or whenever you want to enter, the doors get automatically open. So this is an example of a capacitive proximity sensor. This capacitive proximity sensor is also useful for detecting the specific object in a particular container. So that we'll see next. But the capacitive as well as inductive sensors, they come in the shielded as well as non-shielded way. So this is an example of a, if you can see in this diagram, this is a non-shielded, whereas this is a shielded. Why? Because when you want to collect the signal from the environment, if you want the object to be present exactly in front, then the shielded will be a good example, or shielded will be a good option. But if you want the signal to be collected anywhere in that specific region, like as you can see in the mall, if you keep anything in that particular region, the doors, gets open. So that is an example of a non-shielded proximity sensor. Are you getting this? Right? As far as the inductive proximity sensor, the functioning is different. Again, this is used to detect the objects, but capacitive proximity sensors can be used to detect any specific object, no criteria like material, metallic, non-metallic. But inductive sensors, they are basically designed for ferrous material, right? So the inductive sensor uses a coil connected to an oscillating circuit, right? So to generate a high frequency electromagnetic induction, again, here the concept which is used is the electromagnetic induction. Right. So whenever there is a change in a magnetic flux linked with the coil and EMF is induced in the coil, this is Faraday's law, right? So that Faraday's law's application is this inductive proximity sensor. So the induction changes accordingly, the internal oscillatory circuits is triggered. Okay, so what are the practical applications of this capacitor as well as inductive sensors? Inductive sensor, as you can see in the left-hand side diagram, any metallic object it can sense. So it can be used to sense the metallic objects, their quality, their presence. Even they can be used for counting such metallic objects. If you see on the right-hand side, the capacitive proximity sensors, they are actually detecting the content inside the box. So for example, this is a milk container. So what is present inside that, its quality, everything, because you know that each and every material has a different capacitance. Right. So as per that, you can select a capacitive proximity sensor as per your industry requirement, and it can be used to detect the specific object. Okay. So these are some practical applications of the capacitive and inductive sensors. This is about the proximity sensors. Then one more category of the sensors which is very commonly used in the industries is vision and imaging sensors. So what is a vision and imaging sensors? They are actually electronic devices that detect the presence of the objects or colors within their fields of view and convert this information for the display. So again, the monochrome as well as the color sensors are available. They usually integrate a camera, lights, and controller in a single unit. Okay, so they are employed in many manufacturing operations for quality control, presence sensing, positioning. Actually, what happens, in this vision or imaging sensors, basically they have the additional light control system also, where they have the light rings, they have the lenses, they illuminate a particular object to decide or to detect whether there are some scratches, there are some defects in this. So these are few examples or the practical applications, industrial applications of the vision and imaging sensors. If you can see on the right hand side, there is a sensors fitted, there are some objects coming, right? Those objects are basically vision, and you can see that there is a area sensor. So there are again various different types of vision sensors. One is the area sensor, another is a blemish sensor. So I have discussed few applications here. Area sensor is typically what it is used to detect missing features in a machinery part. So if there is some machinery part which is not present in that, some hole is present or multiple holes are present, so that can be detected by area sensor. Okay. Again, if there is a blemish sensor, blemish basically means what? Flaw or a mark, right? So if you have to detect some flaw in the object, or maybe some scratches on the surface, or if there is any foreign material which is present on some packed food or packed material, that can be detected using the blemish type of sensors. Okay, there is a match sensors. So in a match sensors, what they do, you have some standard image which is already present in your software, right? These sensors, they create the image, right? And that image is again compared with the standard image. And if there is some discrepancies and all that, then that object will be rejected, or if it is okay with that, then it is selected or it is allowed to pass for the packaging. So this is a concept of, again, a match sensor. A sort sensor, this is typically used in a pharmaceutical company, or to keep them in the alignment. Most of the time you can see that the bottles, they don't go when they are traveling on the conveyor. There are multiple bottles which are going. Those bottles, they don't go here and there. They just keep on their path. So how it can be done? It is done by using this position as well as the sort sensors, which actually keep them aligned, right? And at a proper place. So various different types of vision and imaging sensors are used for all such applications. Next category of the sensors is the position sensors. If you can see on the right hand side, the automotive designers and the engineers use these position sensors to measure the important engine parameters. So this is one application. Actually, what are these position sensors? In a simple way, they detect the position, whether a particular object or a wall or the door or a throttle, whether it is at a right position or not. Typical example is, suppose you go in an automobile sector, right? In automobile sector, you want to paint a car, right? So before starting the painting, you should have the confirmation that yes, you are aligned at a proper position, so that the spray paint motor will be started and the car will be painted. For that, these position sensors, they are used for the alignment. There are various different types of position sensors like inductive, capacitive, optical, ultrasonic. Again, inductive uses the concept of inductance. By changing the inductance, the position is detected. Capacitance, by changing the capacitance, the position is detected. So that is the application of capacitive position sensor. So if you see this, smartness of the sensors, whatever things you are learning now in your diploma, or maybe you have learned in the basic science, right, in the 9th and 10th, all these are the practical applications of them. So understanding a particular concept and learning a particular concept is one part, and applying them in the industries, there needs a mind of the engineer, and this is what you have to do tomorrow. So you may be adding some new sensors, right, as per your applications. So industrial processes in the automated production lines use position sensors to make sure that the products are properly positioned before an automatic process step by steps can take place. Even the security cameras, which are used nowadays in for building management system, and even the industries where the safety part, or in a defense also, where the safety part is a crucial role or important thing. There, these cameras, they have the self-alignment so that they can give the optimum view. So this self-alignment is based on the position sensors. Are you getting this? Next part is the motion sensors. Again, they detect the motion, the movement, or a stoppage of the parts and people. One of the good example, rather the first motion sensor was designed in 1960. That was for the burglar. It's a burglar alarm. A motion sensor, is basically detecting that is there any movement in that particular region, and accordingly it generates the signal. So what is the concept of operation of this motion sensor? So it basically emits the radio waves or the microwaves based on your applications needed. So there is a specifically what we can say a restricted area or prohibited area, and it is continuously, there is a sensor fitted, active motion sensor is fitted at one end, and it is continuously sending the radio waves or the microwaves throughout the room. And after striking on the walls and different containers or the objects, they are reflecting back, which are again detected by the sensor. Whenever any person enters into a room, right, the person is also emitting the waves in the microwave as well as the radio waves region. So there is a change in that, what we can say, the frequency. You may have heard about the Doppler effect and all that. So these sensors are what we can say designed in such a way that they will detect a specific frequency depending on if a human person enters, then what should be the shift in the frequency. If any particular object is there, then what should be the change in the frequency. So they are designed in such a way. So this change in a frequency will trigger the signal to the on the output side of the active motion sensor, which is then given to the controller. And then it may be given to the controller, or it may be directly given to the alarm systems or the light. And then the lights or the alarm system will be triggered. This is one application. Another application of the motion sensors is very common. If you go in a specifically nowadays in a walkway or street lights. So basically what happens that whenever you enter in that particular specific area, right, immediately the light gets on. Even the smart automation or the building automation, you might have seen such examples that when you enter into a specific area, the lights in that area gets illuminated, or even if you are entering into the room, the light gets on. So this is basically an example of a motion sensor where your movement is sensed, and accordingly the enabling or disabling of the lights have been done. So again, this is a very common application of the motion sensor. So you can see that how these sensors have made our life very easy. So again, if you go for a next part of the sensor, that is a temperature, flow, level, pressure, you can see that these are the very common parameters which are used in the industries: temperature, flow, level, and pressure. In the right hand side diagram, you can see on the top side, there is an example of a temperature sensor. The first one is a thermocouple, second one is a RTD. These are the common units which are basically used to measure the temperature in the field. So you know the basic concept of operating principle of the thermocouple, that two dissimilar metals are connected. One end is welded, which is sensing the hotness of the object, and the other end is connected to the triggering circuit, so that whenever the hotness or the coldness, there is a change in temperature, that is then sensed, and accordingly the output in the form of voltage is given to the controller. RTDs also works in the same way, but only their output is in the form of resistance. So if you have a controller which is sensing only the signal in the voltage or current form, then you need to have some converters which will convert this output from the RTD in the form of resistance into a voltage or current. And then you have to give it to the controller. So such converters are also most often they are embedded into the RTDs, and you directly give the they give the output in the form of voltage or current. So these are also very commonly used in the in the industrial applications. Magnetic flow meter, which is used to measure the flow. Suppose the water is flowing between the two plates. You can see the diagram that the water is flowing through the that flow transmitter. It is fitted with the electrodes, and a Faraday's laws of induction again is used here, that the voltage is generated whenever there is a change in a magnetic flux link with the coil, and that voltage varies with the amount of liquid which is flowing through this. So accordingly, you can measure how much amount of flow of liquid is there. It is directly what we can say configured in terms of or calibrated in terms of voltage. Say for example, a flow transmitter is designed to measure the flow of 0 to 4,000 liters per hour. Its output is say 4 to 20 milliamperes. Now, whenever the zero flow is there, if you try to measure the output, you will get a 4 milliampere. And if the flow increases, if somewhere it is almost 2,000 liters per hour, you will get 12 milliampere as the current on the output side. And if you get say 4,000 liters per hour, then you will get a 20 milliampere. So current, it is calibrated in terms of current. Whatever is the flow, that is calibrated in terms of current. And the basic principle of design is used in this magnetic flow meter is the Faraday's laws of induction. So you can see that whatever you are learning is, how much it is important. Tomorrow when you will go into the industry, these are the applications. Again, one more, that is a level. Level is again a very commonly used parameter in the industry, or major parameter in the industry. You can see on the right hand side that this is basically an example of an ultrasonic level transmitter. So there is an ultrasonic transmitter which is fitted on the top of the tank. It is continuously sending the sound waves in the range of 20 kilohertz to 200 kilohertz, which are called as ultrasonic waves. Then they are reflected back from the surface of the water or surface of the liquid. Accordingly, the distance of the liquid and the level of the tank is measured. So this is a very common application used in the oil and gas sector, or maybe in a power generation plant where you have to keep or maintain the level of the tank. Pressure, measurement of a pressure. Again, here I have shown the example of a piezoelectric effect. Let me tell you that I'm just giving one example of, measuring the level or measuring the pressure, but there are n number of ways, and n number of different types of sensors which are used, to measure the pressure as a parameter or level as a parameter in the industries. And all these technologies are based on your basic engineering as well as a science concepts, right? So again, here the piezoelectric effect, when you apply the pressure, the voltage is developed. When you apply the pressure on the two opposite plates, the voltage is developed on the other two plates. This is a piezoelectric effect which you might have learned in your college. Okay, so various different applications are using this. Generally, the weight cell, they are also using the same concept, weight cell or load cell. Say, for example, I have to measure the weight of the container, whether it is 500 kg or not. If the container has, or the box has a 500 kg material, then the box is allowed to pass. There, you can use these weight cells or the load cells, which is basically working on the piezoelectric effect principle. Again, there are gas and chemical type of sensors. Generally, where these gas and chemical sensors are used, suppose you are working in the region of nuclear reactor, boiler, where hazardous rays are coming, alpha rays, gamma rays, beta rays, butane, such hazardous rays when they are coming. And if the person has to enter inside that room, right, from the human safety point of view, he should understand that what is the level of the gas present, hazardous gas present in this room. Okay, so for that, these gas and chemical sensors and the detectors are used. Now, what is a very common example is a MQ2 sensor, which I have mentioned here, that you can see that at the heart of an MQ2 sensor, there is a ceramic element coated with a tin oxide. The element is heated. When the element is heated, it emits the free electrons. These free electrons, they are entered into the atmosphere. in the atmosphere, you can say that in the air, if it is a fresh air, the more oxygen is present. And if it is a hazardous, air present with a hazardous gas, or, what we can say, the less amount of oxygen, then what happens that these electrons, they combine with the oxygen, right? And they generate the current, which in turn flows through the sensors. So if the atmosphere changes are present inside that, how the atmosphere will change? By the more and more amount of gas present inside that. So if these electrons, they remain uncombined with the oxygen, the more current will flow. Or if they are more frequently combined with the oxygen, then the current flows will be less. So this particular concept is used here, to measure the amount of gas present. And accordingly, you can detect whether, or you can decide whether to enter into the room, or how to remove that particular. There are sensors which actually helps to, to remove this unwanted gas by some controller, by giving some signals to the controllers. So these are all, various different applications which basically are used in the industry. As a conclusion, what I will say that how to select a sensor. There are various, if you can see, n number of applications, n number of sensors designed for a specific applications. So when you are working with the sensor, the very common question comes in your mind that how to select. If there are so many different types of sensors, how to select them? So very first thing is basically you have to decide the application. You have to decide the application. So what type of application or process you are working with? Accordingly, say for example, if you are working with some pneumatic related components where you have to, material handling process, where you have to segregate the materials. In that case, proximity sensors play a very, very important role. In fact, I'm going to share, small videos with you where you will understand the practical application of most of the proximity sensors, right? So proximity sensors are generally, they are designed in such a way that they come with some fitting for the pneumatic cylinders. So as soon as they trigger, the pneumatic cylinders will get activated. So if you have applications related with the material handling, these type of sensors will be more preferable. So you must decide what type of process you are working with. Second thing, while selecting a sensor, you must understand what is the range and distance. Like as I said that your diffuse sensors, they work in the range of 8 meters. So if you have to sense a particular object which is kept at a distance more than 8 meters, these diffuse sensors will not help us to, to detect that particular object. So you must decide first that what is the type of the applications we are working in, what is the distance within which these objects are sensed. So that is the second criteria. Third criteria is, what type of output current, or, the sensors output is either in the form of current or voltage or resistance. These are very three common way, right? Because these are all electrical signals format. So if you have to give the output to a particular controller, which is actually sensing or receiving the data in the form of current itself, then that sensors must be selected based on the 4 to 20 milliampere range. If they are receiving the data in the form of voltage, then you must decide that, or you must select a sensor which gives the output in the form of voltage. So your output types, your selection of the controller, that also plays a very, very important role in the decision of the sensor. Your response time. Generally, the gas and leaks, which we were talking just now, they take some time for the response, at least some seconds or the minutes. So if your sensor is giving the output only in the range of milliseconds, that means the response time is in milliseconds, then they are not suited for a specific applications. So you have to also see that what is the response time of the sensors, right? And the last one, and which is very, very important, you must see that what type of environment you are working with when you are using that sensor. If it is a hazardous environment, then specific applications or specific sensors may not be working there, right? Say for example, if you are working in a Gulf countries and all that, where continuously in any instrument there is what we can say the unwanted part, and what we can say your small particles, your dust particles, they are continuously coming. Okay. Now, in such cases, your sensors must be designed in such a way that they can work in such environment. So your features or your environment is also playing a very, very important role in a decision of the sensors. So to conclude that there are various different types of sensors, friends, which are used in the industry. Sky is the limit. You yourself can see the applications. In fact, I would recommend you that you just take a tour, just have a walking throughout your building, or maybe along the inside the train, on the railway platform, and just see what problems we are facing. And if you could design some sensors which can make our life easy. So this is what a simple message I can give. And let me conclude. Before conclusion, I being a Sage Automation, what we can say as a part of a Sage Automation, we have our training center at Thane, and we have developed some industrial prototypes where you can see few of the applications of this. So I just wanted to share that with you, and then I will conclude. Okay. So let me share, just give me some time. Okay, this is an example. So here you can see that the diffuse sensors and all the different types of proximity sensors which I have discussed, we have designed one application here, which is a segregation of material. Okay. So here you can see diffuse, capacitive, inductive, as well as through beam and retroreflective sensors, all the different types of proximity sensors. You can see how they are applied here. So this is a capacitive sensor which is rejecting that aluminum object. Now this is a ferrous material, this is an iron object. You can see that the inductive sensor will sense that, and accordingly pneumatic cylinders are activated. And the plastic object is then allowed. Like that, you can segregate the material. This is one. Then another application, let me show you. Just wait. Sorry, wait. Let me show you another application where the level, pressure, and all these, they are also embedded in one instrumentation rig. Yeah. So this is one application of the instrumentation. This is called as an instrumentation rig, which has a level transmitter, flow transmitter. Now here, this is a level transmitter. This is actually sending the signal in the ultrasonic wave form, right? This is your flow sensor. These are the pressure sensors, which are measuring the input pressure of the liquid and the output pressure of the liquid. Here they are all connected, and there is a data signal sent to this PLCs. This is a compact logic PLC, and then that data is also monitored on the HMI on the screen. Okay, so I just wanted to show you such examples that, yeah, this is how the industry is basically, using all these different applications, and the sensors are playing a very, very important role in this. Okay. So with this, I end my talk, and thanks for giving me this opportunity, Pooja madam, and all the HODs, and the Mohit sir, and all the people, and again the students. Very, very thanks to you that you have listened. I hope you have listened this. And if you have any questions, you can ask me. Otherwise, we'll end. Okay. Thank you, Pooja madam. Over to you.
Thank you, sir. We'll take few questions. Is there any question? Sir, actually, very few people are there, but many students are attending this conference through our YouTube link. So there also students are asking few questions in the chat box. So one question was there, like you have mentioned in gas and chemical sensors, one is MQ2 sensor.
Yeah.
So what is exactly that MQ2 sensor and what are the different applications of it? That was the one question.
One application which I was talking about, that one application is, see, basically there is a tin oxide present inside that. It is heated internally. So what happens? It emits electrons in the atmosphere. What we have to detect is a hazardous gas present in the atmosphere. Now, if the hazardous gas is present, naturally the oxygen level will be less. What these electrons they do? The electrons they react with the oxygens in the atmosphere, and if they react with the oxygen in the atmosphere, the current which is flowing through the sensor will be less. Right? The hazardous gas is present, that means it will not react with the oxygen. Like a butane is there, so these electrons they will not react with the butane, so they remain as it is. And that's why the electrons, when they come back again to the detector of the sensor, which is again encapsulated inside the sensor, the more current will flow through that. So if the more current is flowing through that sensor, that indicates that the hazardous gas are present, and the amount of oxygen present in that is less. So it is dangerous part. So that actually triggers the what we can say, the dangerous signal alarm system. That is how it works. This is one application. There are so many applications. Again, I am not see, this is industry is like a sky is the limit. So I'm not a master in each and every industry. So there may be some other applications which are present of this gas and chemical sensors, right?
Any question?
Otherwise, you can also ask me the questions afterwards. You even madam and the Mohit sir have the number and email. If you have any question.
Sir. Yes, sir. If there is any question, then definitely
you can ask. And I also request you to come and visit our training center here, because we have created an industrial prototypes. Students will enjoy to see the real world scenario here. Okay, so you can plan it afterwards. Okay.
Okay, thank you, sir.
Anything else?
Nothing. Thank you, sir. We really enjoyed your session, and it was really simple and fantastic. Thank you, sir. On behalf of VPM's Polytechnic, I'm grateful to you, and thanks for giving your precious time for this conference.
Thank you very much.
Now, I would like to request Mrs. Rujuta Kamri, lecturer, Electrical Power System Department, to introduce our next speaker.
Very good afternoon to all. On behalf of VPM Polytechnic Thane, I welcome our speaker, Mr. Alistair De Silva sir, who is the Director of Absolute Motion Private Limited, for our second session of the conference on sensors in industrial automation. It's my pleasure to introduce such a young and experienced person in sensor technology. Mr. Alistair sir is an entrepreneur with experience in industrial automation and robotics industry. Since inception of his career, he has worked with the top brands in a motion control engineering and have been involved in the core motion engineering development projects. Presently, he is in charge of Prayas education program. His experience in a training of professional engineers in automation and robotics industry. He have trained in the domains of PLC programming, motion controller programming, servo drive commissioning and programming, HMI design, courses programming in brands like Schneider Electric, Mitsubishi, Delta Electronics, Siemens, Panasonic. Currently, he is a team leader of Prayas Education Program, where they are reaching out to the top engineering academia and providing industrial training. Previously, he has worked at the Trio Motion Technology as application engineer, worked with the UK-based MNC Trio Technology in their expansion into Indian market. Then he has worked at a Schneider Electric distributor, Satyam Enterprises, as in charge of sales and application support for the Schneider products for Mumbai region. Currently, he is the director of Absolute Motion Private Limited, heading the Prayas Education Program, where Absolute Motion provides industrial level training in the industrial automations, IIoT, and basic robotics. So it's my pleasure to have an expert from sensor technology to talk on our topic, sensors in industrial automation. I welcome you, sir, and thank you very much, sir, for accepting our invitation. And once again, I welcome you and I request you to proceed for the session. Over to you, sir. So please.
Thank you, ma'am. Yeah, just want to confirm my voice is clear, audible.
Yes, sir.
Yeah, okay. So thank you, Rujita ma'am, for the introduction. I think you've covered almost everything, my whole career journey, I think. And I'll just quickly share my screen also. Yeah, just confirm my screen is visible.
Yes,
Okay.
it is visible.
Okay. So before I start, big thanks to VPM Polytechnic. Thank you for having me. I've already interacted with students. It's great to be interacting with the college again. Thank you, Moite sir, for the invitation. Actually, in fact, one of my colleagues, Mr. Vishwa Shukla, he is actually alumni of VPM Polytechnic. And unfortunately, because he is not present today, I am taking the lecture in his place. But he is also very proud to be an alumni of VPM College and part of our company as well. Okay, so I think looking at the program already, I think most of the sensor theoretical point of view has already been covered. So since you'd like to not repeat things, in the interest of that, I will be concentrating more on the practical demonstration. Okay, so what do I mean by practical demonstration, right? So I have in front of me actually a full kit, PLC. This PLC is actually, I'm going to be connecting sensors to this and basically showing you in real time how a sensor would be connected to a control device. And I'll be sensing different objects, be showing you actually practically how a sensor is going to be working, how we do the wiring. And side by side, we'll be looking also at the PLC software to see the signal is coming in and how we are reading the signal, right? So again, we'll not concentrate too much on the theoretical aspect of things. I think more of a practical aspect would be much more interesting. So I think I was actually present for the previous lecture as well just now. So I was, sir has done a fantastic job in explaining most of the sensors, right? So when I'm going to be talking about sensors, my company Absolute Motion, from the name itself, you will come to know that we are mostly into motion applications. So when you talk about industrial automation, you can roughly classify it into two types. There is process automation and there is motion engineering. Okay, so process automation is basically where you're going to have, things like a water treatment plant or your oil and gas industry, whether there are going to be sensing devices. And there's usually a large amount of IOs, inputs and outputs in these kind of machines. And the second type, which is I think a very emerging field in India, very hot field in India, especially, is motion engineering. Okay, so what motion engineering deals with is moving machinery. Okay, so everything from your bottling industry to FMCG to your packaging machines to probably cut to length steel cutting, wherever you require speed, accuracy, and precision. Okay, that is where motion engineering comes in. Okay, so when I am going to be talking about sensors, I'm going to be talking about mostly I'm going to be talking practically showing you some of the sensors which we have used in the industry and which we feel are very important, especially for motion engineering point of view. Okay, so I have maybe around 4 to 5 sensors with me in front of me. Okay, so we'll be practically seeing the working of each of these sensors, right? So also one thing, since we have been so our company's main business is obviously industrial automation integration. Okay, so we work with companies like Schneider Electric, Omron. Uh, we work with Lenze Mechatronics, we work with Delta Electronics, SMC Pneumatics. So we basically do integration for these companies and distributors, right? So whenever we are going to be executing this in the industry, the whole integration job is going to be usually falls on us, right? And it becomes very important for us to understand how to select sensors as well. Okay, even though our job might only be integration or the programming part, also the sensor selection usually falls on us, right? So I know there might be a lot of students in the audience today, and I'm pretty sure that I always believe that once you sit for a lecture, there should be some outcome out of it. Right? So what I've done is instead of just purely sharing industrial sensors with you, I'm going to be practically showing you industrial sensors, but I'm also going to show you the hobby equivalent of it. Okay, so obviously you are not going to go out and buy a 15,000-20,000 sensor. You will probably buy a sensor which is compatible with a Arduino or a Raspberry Pi, right? So I'm going to show you both sides, right? So every sensor I talk about, I'll be showing you both sides. Right. So let's, we are already a little late, so I'll start straight into the lecture, right? So as you can see, these are some of the sensors which we are going to be covering today. And you can see most of these are actually hobby sensors, right? If you look at them, they are all the hobby type sensors, something that you can integrate with your Arduino, Raspberry Pi, your ESP32 board or something like that, right? Now, to start off, at the very basic, we have to understand that there are generally two types of sensors. One is your active type and one is your passive type. Okay. I found this very nice picture from RealParse. Okay, so I decided to use this only. Active sensors are generally sensors that do not require an external power supply, right? So over here, you will see that there is a temperature sensor over here, okay, an RTD, which is directly giving a reading straight to a in millivolts to a meter. Okay, so as you can see over here, there is no power supply given externally to this sensor. Okay, so these are called as active sensors, right? And passive sensors are the more common ones. Okay, where basically you will require to connect a power supply externally, right? So the sensor has to be powered on first, and then after it is powered on, it can give us something. These are generally all the sensors actually which I'm going to show you are except for one, I think, are all passive sensors. Okay. Okay. So now I don't have a temperature sensor, unfortunately, to show you today. Okay, I'm just going to explain it. What is a temperature sensor? So your temperature sensor is, as the name suggests, it is going to be detecting the temperature of whatever object you want to detect. Right now, the thing about temperature sensors is that there is a large amount of selection required because there is a huge range of your RTD type. Okay, which you see on the right, your industrial RTD type is going to differ. Okay. So sometimes you might want to maybe the same sensor, for example, cannot be used to detect -50 to 0 degrees. And as well as maybe let's say 0 to 100 degrees. That means hot and cold, right? So generally you will not find this mix. You will generally find sensors which are suited for a particular operating range, right? So again, I said there are going to be, I'm going to show you both sides. So on the left side, you will generally, this is what you will see as the hobby sensor. Okay, this is what your hobby temperature sensor looks like, right? And as you can see, definitely mounting the sensor on an object is going to be a little difficult, but at least the ambient temperature and things like that, usually these sensors are used for that, right? So your ambient temperature or anything like that. Whereas your RTD type, as you can see, it is designed to be mounted on a particular object, right? So this is the sensing part is going to be screwed onto, this is, you can see a screw here, It's going to be screwed onto an object where you're going to get it, right? Now, when you talk about the with the signal which you get from these sensors, generally you will not have a sensor directly connected to a PLC. Okay, there is going to be a temperature module which is going to be connected. Right now, the reason for this is that generally it is going to be you will need to run a PID loop. Okay, you will need to run a PID loop. That is how you're going to be able to control the heat, and generally it is always used with a heater. Okay, so the heater is going to apply heat. The temperature sensor is going to detect the heat, and to control this temperature, right? How much heat applied to how much we are reading through the RTD, we are going to require this. Okay, so generally it is we have a special module which is usually called as a temperature module, which is connected in conjunction with a PLC, right? And this is how we use it in the industry, right? The signal which you will get from this RTD is obviously not a digital signal, right? So sensors, again, there are two types. One is going to be digital, which is going to give you either an on or an off. Very simple, right? Either it will give you on or it will give you off. This is not that type of sensor. This is going to give you an analog value, right? So it can be 4 to 20 milliampere, or it can be in voltage 0 to 10, or it can be in some other form. Okay. Now we come to proximity sensors. Okay, so the good luck is that I have some proximity sensors with me, right? So I have a inductive, I have a capacitive. Okay, so I have these two sensors with me. Now, depending on what you want to sense in the industry, right? What is your material and what is your range? Okay, you are going to be choosing what type of sensor you would like to use, right? So your inductive sensors is going to be detecting your materials such as iron, steel, aluminum, copper, materials like this, right? So any metal detection which needs to happen, that will be your inductive sensor. Okay, I will show you a practical demonstration of the inductive sensor right after this. Okay, usually the sensing range is between 4 to 40 millimeter. Okay, so depending on how far you want to sense, right, you will have to select the sensor. Now, some of the sensor actually have an adjustable knob on the sensor, right? So you can actually adjust the sensing. Okay, now those will obviously be a little more expensive than your regular ones, right? So still 40 millimeter is quite a close. Okay, so any close we call within let's say 60 to 80 millimeter, we generally call it as a close range, less than 50. So any close range detection of a ferrous material. Ferrous basically means iron content. Any detection of ferrous material, you will require this inductive sensor. Right? Now, supposing we don't have a metal to sense, right? We want to detect an object that is non-metal, right? For example, it could be liquids, granules, plastics, glass, anything like this. Right? Then you will use a capacitive sensor. Okay. So again, capacitive sensor, I have one sensor with me, so I'll show you how it's going to work. Any close range detection of non-ferrous material. Okay. Now, capacitive sensors, generally you will find that you will generally have a adjustable knob. Okay, you will have an adjustable knob, but again, it all depends on the cost. Okay, if you have a low cost sensor, you will not have that adjustable range. Okay. Then we have photoelectric sensor. Okay, so photoelectric sensors is going to work differently from your inductive and capacitive sensors, right? Photoelectric is, as the name suggests, it is going to use light as a means of detection. Okay, so any light, it basically emits a light. Now, in the case of photoelectric sensors, you also have ones with reflectors, without reflectors, things like that. We are talking about the ones without reflectors, right? So in your photoelectric sensor, there will be an emission of light, and there will be a receiver of the sensor itself. And when you get back the signal, depending if there is an object in front of it or not, it will then give you an on or an off signal, right? So photoelectric sensors usually, the good thing about it is that you can sense objects very close. Okay, so you can even have up to 0.5 millimeter detection as well, very close object. And you can go right up to 60 millimeter. Okay, so very wide range. Okay, the great thing about photoelectric sensors is they are almost 99% always sold with a range dial. Okay, so you can actually adjust the range, right? And based on that, you will be able to get the signal, right? Ultrasonic sensors. Okay, so wherever you have, supposing you want to use photoelectric sensor on something like a transparent material, such as glass, cellophane, foam, any liquid or some powder which is transparent or something like that. In that case, obviously a photoelectric sensor, because it is based on light, it is going to melt out, right? So in that case, we will have to go for an ultrasonic sensor, right? So as the name suggests, ultrasonic sensor is going to use ultrasound, and the range is generally between 3 to 30 millimeters. Okay, so the range is not as good as the other sensors, but again, ultrasonic sensors are used for very specific materials. Okay, so now one more thing important about ultrasonic sensors is that supposing you have two transparent mediums, you will have to understand that it is only going to sense the first medium. For example, supposing I have a bottle of water and the bottle is transparent. Okay, so ultrasonic sensor would not be, if I want to detect the bottle, I can use an ultrasonic sensor. Okay, but if I want to detect the liquid inside the bottle, then I will have to use a different sensor, right? Because my ultrasonic sensor is going to sense the bottle, not the liquid inside. Okay, so for that, I'll have to use another sensor. They are called as fiber optic sensors. We'll talk about that. Okay, so these are your proximity sensors. Okay, let's talk about your each of them one by one. I think proximity sensors are the most common, and I think the most used in the industry as of now. You all will see this everywhere. Okay, so I think we'll go a little bit deep into these. When we talk about inductive proximity sensors, this is generally how it works. Okay, so again, like I said, you are going to be detecting ferrous targets. Ideally, it should be mild. Okay, but ideal condition does not happen in industry, right? So it will detect in any ferrous. There should be some good amount of ferrous percentage in the material you are sensing, right? So ideally mild steel. Now, there are four major components in this. There's a ferrite core with coils, there's an oscillator, there's something called a Schmidt trigger, and there's an output. Okay, so how this basically works is that as soon as an object enters the magnetic field of the sensor, okay, you can see here there is going to be an object. Okay, there are going to be some small electrical currents. They are very, very tiny electric currents. Okay, they are called as eddy currents. Okay, and those are induced on the metal surface. Okay, so what is going to happen is that this is going to change the reluctance. Okay, this is called as reluctance, which is basically you call as the natural frequency of the circuit, which is going to reduce the oscillation amplitude. Okay, so this Schmidt trigger, which is located here, that second stage, right? You can see it here. This is going to respond to these amplitude changes. Okay, and according to that, it's going to adjust the sensor. Now, obviously, because the electrical currents are so tiny, they definitely have to be amplified. So then we have an amplifier so that we can actually give the signal outside and we can sense that signal, right? So inductive proximity sensor, like I said, I would like to show a practical demonstration of it. Okay, so just bear with me while I just shift my position a little bit. Right? I'll turn off my camera for now, okay, because I'll be showing you another camera right here. Okay, so I have in front of me PLC. So if for those who don't have time, to give a whole brief about what a PLC is. But a PLC is basically a programmable logic control. This is what a PLC actually looks like, right? And this is actually a company called as Delta Electronics, one of the very famous companies for automation in India. As you can see, so I have basically mounted it on one of my training kits. Okay, so this is my training kit. As you can see, there are various devices already mounted here, right? So none of these are sensors, okay, except for this. Okay, all of these are actually buttons. We are not concerned about this part, right? But we, I wanted to just explain the working basically, what I'm actually connecting. So obviously this whole thing has to be powered on using something. So you can see this little black box over here is actually your supply, right? So like as I told you, sensors, passive sensors will need to be supplied by power externally, right? So this is where actually the power is going to be coming from. So this is my 24 SMPS. Okay, so my power, I'm giving power from my wall socket behind there. It is getting connected at the bottom here, line and neutral. And this is converting the line and neutral to 24 volt DC. Okay, so in the industry, most of your sensors, 99% of your sensors, which are digital sensors, are going to work on 24. So that is the industrial standard for sensing. Okay, so you can see that this plus plus minus minus is basically 2 ports for 24 volts and 2 ports for 0, which we are going to be supplying to our sensors, right? Now, after the SMPS has been supplied with power, then this power is distributed along this whole kit. Right? So this whole kit now has, each of these components has 24 volts, right? So the LEDs have 24 volts, all these buttons have 24 volts. Okay? What I've done here to simplify matters, we have done something very simple. I've taken a terminal block. Okay, I've taken a terminal block and have connected 24 volts. Okay, I've connected 24 volts here.
So just one request, can you please maximize the VLC media player screen so that...
Actually, ma'am, this is the largest it can go. So,
okay.
Yeah. It is coming from my phone actually. So, portrait mode. So, otherwise it will not come in the frame.
Okay, fine, sir.
Yeah, I'll try to just increase the go a little closer so everyone can see.
Okay.
Yeah. So, we have this terminal block. We have 24 volts here. We have 0 volts connected here. Okay, so 24 volts is red, 0 volts is blue. Very simple to understand. And this is going to my PLC input. Okay, so this is actually going to the PLC input right here. Okay, so this is where I will connect my sensor. The signal of the sensor will be connected here. So on this side is where I will connect my sensor. Right. So now if I bring my sensor into my frame, let's move this a little. This first sensor is the one which I'm talking about, which is an inductive sensor. Okay, you can see this is an inductive sensor, right? So this inductive sensor actually again works on 24 volts, and it is a PNP sensor. Not go into what is PNP. For those who know what is PNP, it's going to give a 24 volt positive signal. Okay, so 24 volt signal to my PLC. Now, what is the wiring is that I have already connected this sensor. The next sensor I'll be showing you. So here there are 3 wires of this sensor. You have brown, blue, black. Okay, so brown is, this is generally an industrial standard where brown is your 24 volt, blue is your 0 volt, and black is your signal, right? So this is how I have connected it, 24, 0, and this is the signal, right? So these two are actually powering on this sensor. Okay, this is powering on the sensor, and this black one is actually giving the signal of the sensor. So when the sensor turns on, then only this black will give me a 24 volt signal, and this will then go all the way to my PLC. You can see it connected to my PLC over there, right? Now, let me just show you the working now. Okay, so if I actually try to sense my hand or something like that, you will see nothing is happening, right? You will see nothing is happening here. But if I take something like a screwdriver, which is a metal object, and I put it in front, you will see that the light has now turned on. You can see the yellow colored light turning. Now, as I said, any ferrous material, right? Any ferrous material. So this is actually anodized aluminum, right? This, my kit over here is anodized aluminum. So if I even put this here, you will see that I'm getting a signal around, right? So now, how do I actually see the signal? How do I know it's coming to my PLC? So I'll just quickly open up my software. So this is my PLC software actually, where I have connected. And just a second, I just need to see if it could be actually connected. Just give me a second. Yeah, okay, so it is now connected. So I don't have time, unfortunately, to explain PLC programming today, but all you need to know is that I have taken an object here, which is basically my sensor reading, right? So in the industry, when we write logic, how do we know in the program that our sensor is engaged? So this is called as ladder logic, right? And if I actually just take my sensor and sense it, you will see that inside the program, it is also going to turn, right? You can see it's turning on. You look at the X2 variable, that is, it is turning, right? So this is my first type of sensor. I'm just going to, just for safety, I'm going to turn off my PLC now. And this is about your inductive proximity sensor, right? Now, the next type of sensor is your capacitive sensor, right? Now, this is again going to work differently. Capacitive sensors can detect both metallic and non-metallic. So basically, the target does not have to be ferrous. Okay, can be anything, powder, granulate, liquid, solid, whatever it is. Now this is ideal for things like tank liquid level detection, hopper powder level, things like that. Okay, any object, basically any object that is non-ferrous and you want to detect, these are perfect. Now how it works again, there are basically two conduction plates which are housed in the sensing head. Okay, and they are basically positioned to operate like an open capacitor. So we are trying to actually emulate a kind of a capacitor over here, right? And just like inductive sensors, these plates are linked to a Schmitt trigger, an output amplifier. Now, when the target enters the sensing zone, okay, the capacitance is going to increase between these plates. Okay, so this again, the Schmitt trigger is going to detect this minute change in capacitance, and an output signal is going to be created. Okay, so this is basically how your capacitive sensor is. Okay, now capacitive sensor. Now I need to do this quickly because I want to stay on time. Okay, so I'll just try to quickly show you how you would connect it, right? So I'm going to remove this inductive sensor. We don't require this right now. Okay, so we'll just remove this sensor, keep it to the side, and we'll go ahead and connect our capacitive sensor. So you can see this is my capacitive sensor, right? It looks like this. It's a Panasonic sensor, right? Again, this is a 24-volt output sensor, right? And again, there are going to be 3 wires, right? You can see 3 wires over here. Now, just like the previous sensor, it's going to be brown is going to be your 24. Now, on this sensor, actually, they actually write it over here. Okay, so I'll just try to show you if my camera can focus. BN basically means brown, which makes it, they are telling you very clearly here, put 24 volts. Your BU is blue. They are telling you, please connect 0 volts here. And your BK is black, which is going to be your, okay. So we have got our instructions. So brown is 24 volts. So we'll just go ahead and connect 24 over here. Okay, so this 24 volts is basically used to power on the sensor, right? So we are basically connecting things to power on the sensor. Unfortunately, I will need to just shift my kit a little forward. Yeah, so removing this and connecting this brown over here, right? So just connecting it inside here, right? So this is actually by default, they strip the wires in this way, right? You can see a very, the way they strip the wires is by from the factory. This is a brand new sensor. So this is how they actually strip the wires. They strip in the middle and they leave a little bit of covering at the end, right? So they do this for easy wiring. If you want to just twist it on some correct wire and just tape it. Okay. This is the second one. This is your 0 volts. Okay. The last one is your signal. Okay. So this is going to be your signal wire. Again, I'm just connecting it to the PLC signal. Okay. So our terminal block is just being used as a middleman basically between the two, so that we can easily connect them. Right. So again, powering it on. So I'll just power it on quickly. And you can see that the sensor has turned on, right? So sensor has turned on, and we can go ahead now and again look in our program and see whether it's working. Right? So in our program, you can see that the sensor is here in front of me, and if I sense anything new, okay, if I sense anything even my hand, okay, you will see that the sensor is going to sense, right? So let me just show you the range. If I actually go a little bit, I take a bottle like this, you see the range. So approximately this should be around 50 to 80 millimeters. So yes, you can see that the range is quite, it's around distance, right? So if you actually calculate this distance, you'll probably find it to be around 50. Okay. So you can see that compared to the inductive, this was actually the sensing distance is quite large than the inductive sensor, right? It doesn't mean that you don't get inductive sensors that can sense the distances. It's just that this particular sensor is. So again, it can, anything can be sensed. You can see again there is a usually an indicator on the sensor here, which is going to give you an off signal, and it can detect anything. It can detect the bottom or anything like that. I believe someone's annotations is turned on, which was writing on my screen. Can that please be turned off? Any admin can turn that off. Let's disable it on my end. So this is about your capacitive sensor, right? If I can figure out how to remove this annotation, someone by mistake, I think, has put this red color mark on the screen. So this was your capacitive sensor. Let's go on to the next one. Ultrasonic. Again, I don't have an ultrasonic with me, so I'll just talk about it quickly. This is what your hobby ultrasonic sensor looks like. We are going to be giving out sound waves, right? Object is going to be here, and it is going to be a reflection of these waves. Okay, and color and transparency does not affect these ultrasonic sensors, right? So it doesn't matter if color transparency is there, doesn't matter. Okay, so this ultrasonics are generally used for if you need to detect clear glass. Okay, so obviously capacitive would not be a good choice for that. You use ultrasonic for that. Distance measurement, fluid and granulate level control, paper, sheet metal, wood stacking, things like this, you would use an ultrasonic sensor. Okay, so this is generally this HC SR04. This is what you will actually get for your Arduino. Okay, so just so you all know. Again, just to give you an idea of industrial what they look like. So your industrial sensors generally look like this, proximity sensors, and your hobby sensors will generally look something like this, right? So I'm sure that people have seen this IR sensor and other such things. Okay, so this is generally what you will see for your hobby type sensor. Okay. Now we have light sensors. Okay, so light sensors, also known as photo sensors. Okay. The one which is available generally today are the LDR types. So, what is the property of an LDR? Basically, the resistance. It is a resistance-based sensor, so it is going to give you a output in the form of resistance. The resistance is inversely proportional to the intensity of the ambient. Okay, so the intensity or the luminosity of the light, basically, in lumens. Okay, when it increases, the resistance decreases. Okay, so it is there's going to be some X resistance, and there is inverse relief, right? So these are analog sensors. Okay, so obviously these are not going to be like, now what did I mean by 1 and 0 sensors? As you all saw before, 1 and 0 sensors are when you're getting either on or off, right? That is your digital sensors, right? Here we are talking about an analog sensor, right? So this is where your light sensor is going to be an analog sensor, and that means you're going to get value into your case rather than just getting a 1 and 0 sensor, right? So what value are you going to get? You're going to get the resistance, right? So the lesser the resistance, the higher is the intensity of that. Okay? So these are your light sensors. Now color sensor, this is actually one of the most interesting sensors, and I would like to spend some time on this sensor. One of my favorite sensors actually. Okay, and it is used, very, very interesting sensor, used very widely in the industry, right? Color sensors are used for color sensing application. Okay, so whenever you want to identify difference in colors, okay, so industrial object tracking, difference in colors between paper or something like that. This is where you would use a color sensor. These sensors are also called as print mark. Okay, they are also called as print mark sensors. And the reason I will share with you. Okay, so this is the interesting part. Now I'll just open up my camera again, right? So you have, you might some of you might have been looking at might have if you all have good observational skills, you might have seen this chip packet on the right side. It is not because I was eating it is because I kept this for a demonstration. Okay, so this chip packet basically just give me a second. With my camera, yeah. So this chip packet basically, the reason I've taken it is to show you where these sensors are. You know, the good thing is that I have this sensor with me, so we'll practically see. This looks like very much like a camera lens, as you can see here, right? So this is how the sensor looks like, right? This is again, I believe it is a sonic sensor, LX111P. Okay, and again 24-volt output. It's going to be a digital output, and where is this going to be? Where is this used primarily? Okay. A large amount of print mark sensors or color sensors are used in the FMCG industry for packaging. Okay. Now, if you ever looked at your any chip, you look at this chip packet, Tasties looks, okay. You'd always notice that every single packet is going to be the same, right? And this is because of motion engineering. This is because of motion engineering, because we are using devices like servo motors and print mark sensors, sensors, to ensure that this length is going to remain the same, constant. So if you've ever seen, I'll just increase the size of this object. Okay, so you can see this is actually the roll. Okay, so even if you have something like a bottle, okay, you have something like a bottle. This is a Duke's soda bottle, right? The label which is applied on this bottle is actually, is going to be in a roll form. Can you see this? There are the rolls of labels over here, right? And if you notice, if you've observed all these packets like chip packets, Windows, Bisleri bottle, Daily bottle, Coca-Cola, you will always find. Let's minimize this again. You'll always find that there is going to be something called as a print mark. So if I have to see where the print mark is here, I'll just quickly just peel this back, and you will see there's a white mark. Okay, so a print mark is a small little mark, okay, which is going to be used to identify when the label starts or ends. Okay, so you can see it over here very clearly. If you look at this whole strip over here, you will see blue. Okay, you will see blue, and only where the print mark is going to be suddenly a white strip. Okay, our pocket. Okay, let's see if we can identify where this is. So if you look everywhere, you will probably not find it. But if you know where to look, it is generally on the inside of the packet. Okay, so you will see here again, there is a print mark of black color, right, which is over there. Now, the challenge is that obviously, if you can see there, the print mark has to be detected. That means when it is white color, it shouldn't be detected. It should be off. As soon as this black, it should be detected. So now we need a very special type of sensor to do this. Okay. So again, I'm going to show you the wiring of the sensor. It is very simple, just as the previous one. So I'll just quickly remove the wiring of the previous one, remove the wire, and connect my print mark sensor. Removing this, connecting the print mark sensor. Now again, the print mark sensor, we'll have to look at the wiring. Okay, so if we look and practically see, we will see that it is written very clearly. Brown is plus. Brown is your plus, which is basically 24. Blue is 0. 24 brown, blue, 0 volts, black out. Okay, so it's the same tandem as the other wire. So 24 out. Okay, so we'll connect the brown first. It's connected over here. This is going to be giving 24 volts to our sensor, so it can get powered on. Then we have our blue, which is going to be our 0 volts, right? So let's connect that as well, right? So that's going to be connected to our 0 volts. And finally, our signal. Okay, so this pink wire is not going to be used. That is used for something else. We'll not discuss that today. We'll get a little confusing. So this black wire is actually your signal. Okay. So now we have connected our print mark sensor. Let us just turn on the PLC. We will see that it is turned on. Okay. Now this has to actually be set. Okay, so if you actually see there's a light being emitted, this right. So if you actually look, you can see there's a green color kind of laser kind of emitting. And this is actually what is going to. Now, if you notice, if I actually connect my PLC, you can see that the signal is already on, right? That means it is not set yet. Okay, we have to set this sensor. Now, first, let us try to set it for this bottle. Okay, so if we go to the bottle, we want the bottle to be sensed at the white part. Okay, so off at the blue part. Okay, so when it's sensed at the blue part, we want it to be off. So we have a selection here. It's a very simple sensor. When you click on off, okay, when you click on off, you will put it at the off position, and you will just allow it to detect. So let's just, okay, I think you have to set the on first. Just click on on. Okay. So this is my on, which is white. And my off will be off. Just a second. Yeah, so as you can see, when I on the white color, it is coming on now. As soon as I move it, it is turning on. Okay, so it's really difficult to see. I'll try to move it a little closer. So you can see the beam of light, basically your red beam of light. When it's on the white part, it is coming on, right? And as soon as it goes on the blue part, it's turning, right? So that has set it successfully for the blue. Okay? Now, if I want to set it for this, I can set it differently. Okay, so this was now, because now this is exactly opposite where the white should be off, right? So my on I'm going to set to the black, right? Right, and this is my on, and my off should be white. So on the black, you can see that the green color sensor, you can see that the sensor is on. And as soon as I move it to the white part, it's going to. Okay, now it is set for this particular. So this sensor usually now this is the simple version of the sensor where you're detecting open. Okay. You also get sensors which can detect a range of. Okay, so you can have maybe 3 or 4 colors or more. Those sensors are a little bit complex. They are going to require some. Okay, so you not get into that. That definitely requires much more programming. But the 90% application you see, you will see the sensors being used in the FMCG. So every single Bisleri, Bailey, Coca-Cola, Kurkure, Haldiram packet, everything, almost every packaging application, okay, any FMCG good which you are consuming is going to have these print sensor mounted over there. Okay, so I hope that the explanation is clear. Right, so we'll move on to the next one. Okay, we have humidity sensors as well. Okay, so humidity sensors is something which I don't use personally much in the industry, but I have seen it being used in hobby projects, which is what we do. Okay. So things like weather monitoring systems, you need humidity data. Maybe some kind of machine also where the panel cannot have any humidity. The humidity in a particular room has to be measured, or maybe there are some types of powders for which have to be packed. For example, chili powder, turmeric, and things like that, where the humidity of the particular room should not exceed a certain amount, otherwise the powder will start to get lumped. In that case, they generally have humidity sensors in the room, right? Now, all humidity sensors generally they will measure the relative humidity. Okay, so the water content in the air to the maximum potential of air to hold water, right? So air has a particular potential to hold water, and it cannot go beyond that, right? So because this relative humidity is very much dependent on the temperature of the air, almost all humidity sensors can also measure temperature as well. Okay, so it is generally used together, temperature and humidity both, right? You get capacitive types, resistive types, thermal conductive types, right? And if you are using hobby sensor, okay, hobby sensor, you would want to use the DHT11 and DHT. Okay, these are the very frequently and cheap humidity sensors used in when you are doing Arduino ESP32. This one, the first DHT11 is a resistive type. The DHT22 is the capacitive type. So depending on your application, your industrial sensors are expensive. Okay, so your humidity sensors in your industry are quite expensive. They look something like this. They are going to have you can see their T and H. Okay, so your T over here on the top is your temperature, H is your humidity. So generally, it is the same sensor detecting two things. We have pressure sensors as well. Okay, so in case we need to detect the pressure of some gas or liquid, basically, this is where we would use a pressure sensor. Now, pressure sensors are generally, if you know, most of the machines in our industry today are powered generally by two things: electricity and the other is air. Okay, so we actually use air a lot to power most of our machines. If there is any pneumatic or hydraulic action required, you are going to have some kind of air intake. Okay. Now, when you're going to have air intake, you would also want to measure the amount of pressure which is going to be in the. Obviously, you'll require pressure to do some force work, which does force, right? So that pressure is going to be measured in. Okay. So generally, for applications in machines, I generally see 8 bar being used for FMCG typical machines. So you have 6 to 8 bar generally being used. And that is where you're going to be using your pressure sensor. Okay, so again, in hobby, you will it will look something like this, where a pipe can be connected to this over here, right? See this here, and your industrial pressure sensors look something like this. It doesn't have to have a digital display; can have an analog, normal like analog watch display, be like. Yeah, now Hall effect sensor, this is again, I find this sensor to be interesting because many people are actually, many of the hobby community, your ESP32 device. So your ESP32 can be controlled using your Arduino IDE itself. Okay. So just to show you, just give me a second, I'll just take out my ESP. The ESP32 hobby board looks something like this. Okay. ESP32 looks like, and it's very cheap. It's around say 3 to 300 rupees. It is actually one of the most used boards because number one can be controlled using your Arduino IDE. Okay, so very simple to program. Second is that it's cheap, and the third is that it has inbuilt. Okay, so this Wi-Fi module, it has Wi-Fi inbuilt, so that most of IoT applications can be achieved using this. Okay, so this is the reason why this is the go-to board for IoT application, cheap, low-cost IoT, right? So very important board to know. Now the reason why I'm showing you this today is because this ESP actually has a Hall effect sensor inbuilt. Now, Hall effect sensors work on the principle of magnetic effect. So, magnetic field present. Now, again, doesn't necessarily have to be magnet outside, right? It can be your magnet can be a physical magnet. It can also be an electromagnetic field. Okay? Now, if you all know, most devices, most electronic devices are going to have some kind of electromagnetic field around. Okay? So, if you look at your computer running, you look at your chargers running, and even this kit in front of me, it is going to generate some electromagnetic. Uh, all magnets basically have two characteristics generally. Okay? One is your flux density, one is polarity. Okay? So polarity, everyone knows north and south pole of all magnets, right? Hall effect sensor output will be the function of flux density. Okay, so we'll not go into the working, okay, because it is going to take a little bit of time to explain this. But I just want to show you talk about the application. Okay, so application is generally where where something like GPS detection, speed detection, the angular position of certain devices where you want. One very important, very surprising application is actually your car seat and your seat belt. Okay, and for airbag control, wheel speed detection, things like that, your ABS. Okay, so it is used quite a bit in the automobile industry. Now, if I just want to show you how this works, there is a very simple code which is by default present in the I've already installed it. I just go to the serial plotter. This is basically plotting the reading of the sensor. Okay, so you can see right now it's hovering between around 18 to 20 continuously. Now, if you just take the sensor and move it a little bit closer to something, you will see that it's going to change. Can you see it's changing suddenly? Right now, it is spiked suddenly. Right. So as I move it towards the SMPS, for example, it's probably going to increase. Right. You can see that it has increased. So it basically is detecting your electromagnetic field of wherever we are actually getting, right? So if I move it next to the sensor also, you will see that there is going to be a minute change, right? So the sensor is here, minute change in the field, right? So this is your Hall sensor. Okay, now this is again accessible to you as a student. Definitely it is accessible to you. Why? Because it is inbuilt in your ESP32. So if you have an ESP32 board, very cheap to use this in your applications. Very interesting. Okay, I have a few other sensors which I will talk about quickly if we are getting out of time. One is your load cell. Okay, so again, I'm talking about load cell. Why? It's because it is used extensively in the FMCG industry. Okay, so this is actually how your chips are. Okay, if you ever notice that Lay's, when they say they're giving you 50 grams, they don't want to give you more than 50 grams. Okay, they want to save their money. So they will use a device such as load cell to measure the weight of the chips they are going to be putting. Okay, so this is actually called as a multiware. Okay, this device on top. The chips are fed on the top, and then there are each of these bucket actually have one load cell. Okay, so as soon as there is a vibrator, the chips are going to be vibrated into these buckets. Then based on the combined combination of these buckets, the machine will open up a flap over it. So when it opens up the flap, it is going to open in such a way that it will drop only 50 grams of material. Okay. So for example, if there is 20 grams here, 20 grams here, and let's say 10 grams here, it will open these 3 buckets. Okay. That is a simplified way of explaining it. There are actually 16 buckets. Sometimes there are 24 buckets. So definitely the logic becomes very complicated, right? But in a nutshell, this is what it's used for. Now, this is obviously for low weight. You also have high weight measuring applications. Like depending on that, your load cell module is going to change. So you have different types of load cells: beam load cell, single point load cell, cohesion load cell, various types, right? And your hardware is going to change based on that. Again, your load cell is going to give you either a 0 to 10 analog voltage, or it's going to give you a 4 to 20 milliamp current. PIR sensor, again, another very very popular sensor in today's projects. Okay, I see a lot of engineering students using PIR sensors, right? Now, PIR sensors basically are going to detect generally the presence of an object, okay, a person moving, right? So, for example, a best example of PIR would be a door sensor. Okay, so if you want to detect, if you have seen the automatic doors in mall, where when a person comes in front of the door, the door is going to automatically open. PIR sensor is going to be used for that, right? So there is going to be again there are going to be like a detecting area, okay, which is like a beam of light, which is going to detect an angle of some sorts. Okay, and whenever a warm body like a human or an animal, so first it will intercept the first half of the PIR sensor. Okay, this is going to cause a differential change. Okay, usually it's a positive differential change, and when the warm body leaves the sensing area, reverse happens. Sensor will generate a negative differential change. So the change in pulses is what is actually being detected here, right? So generally, any warm body, any human, animal, something like that, the PIR sensor will detect. Okay? Again, I'm showing you the hobby variant of this. This is what your PIR sensor is going to look like in the hobby variant. Okay? Again, a very economical sensor to purchase, right? This is where your detecting area. You can just mount this on a door or something, and you can control the door or anything like that. Okay, so this is your PIR sensor.
So sorry to interrupt. Can you please conclude in next 5 minutes because of stipulated time period?
Sure, yeah. I'm already at the end, so I will anyway conclude in 2 minutes.
Okay, fine, sir.
Yeah. Okay. So now accelerometer gyroscope sensors are generally used now in your mobile phone. For example, you will have your accelerometer and gyroscopic sensors. Gyroscope generally can sense your rotation, whereas your accelerometer basically can detect your change in position, velocity, vibration, things like that. Okay, so I'll not go deep into this. Okay, since we don't have enough time. And last sensor, which I feel is very, very important from the industrial perspective. Again, I have this here. I would have given a practical demonstration, but I don't think we have enough time for that. This is an encoder. Okay, so if we need to have measure position of a particular object, okay, like something like a conveyor. So supposing we have a conveyor, we have a simple AC motor, and the conveyor is rotating. We actually need to detect the position of that conveyor or the speed of that conveyor. In that case, we'll use an object like an encoder. Okay, so this is my encoder shop here, right? And this is actually going to generate some pulses in my PLC. So maybe some other time I can show that. This is actually mounted onto my kit at the side. You will see that if I turn it, you will see that the encoder is mounted at the side, right? So encoder again is actually like a sensor within a sensor. Okay, so it's not really, I would not really call an encoder as a sensor, but it still comes under instrumentation, which is why I decided to, right? In an encoder, there's going to be a photo sensor, there's going to be an LED. Okay, the photo sensor is going to detect the LED, and there's going to be a disc with some switches on it. Okay? So as the disc rotates, as the shaft of the encoder rotates, that is how we are going to get pulses in our PLC or controlling device, and that is how we will know that the conveyor is moving, something like that, right? So yeah, so just to conclude, just adjust my quick camera again. Yeah, just to conclude, I will say that in terms of selection of sensors, very important to understand selection, and I would say more than that is to understand how sensors actually work. Okay, so like just by trust me, as an automation engineer myself, I will tell you that just by learning the theoretical aspect of sensors doesn't mean that you can go into industry and just implement it. There are a lot of factors which you'll only come to know when you actually use it. Okay, so hopefully I've tried to give you a good practical demonstration of how we connect sensors and how they are used. Hope that was useful to everyone. And I think we can conclude over here, right? Since we are running out of time.
Thank you so much, sir. Actually, the session was very much wonderful because you have shown the things practically, and this will really going to help to our students in their future. On behalf of VPM's Polytechnic, I would like to thank you, sir, for giving your precious, valuable time for our conference. Thank you so much.
Sure, it was a pleasure.
Now some students from our institute are going to demonstrate a project. So I would like to invite Shreyas Avhad and Saurabh Dubey from third year instrumentation department.
Hello, I hope I'm audible.
Yes, you are audible.
Yeah, can I share my screen?
Yes, yes.
Yeah, okay. So, I hope my screen is also visible.
Yes, it's visible.
Yeah. Okay, so firstly, I would like to introduce myself. I am Shreya Shawat, studying in TYIS, third year instrumentation. And this is my classmate. He is Saurabh Dubey. He is with me for this presentation. Actually, I have two more friends of mine doing this project. They are Tushar Sharma and Prem Bauskar. Due to some medical emergencies, they are not present over here. So anyways, let us start with the presentation. This is our IoT-based environment analyzation project. To measure is to control. So here are the table of contents. And moving on, firstly, I would like to introduce what is the need of IoT in environment. So Internet of Things is basically called IoT in short form. IoT has a large role of play in the future of the smart cities and also in the industries. In industries, IoT is basically known as IIoT, which is industrial IoT. IoT can be used practically in many scenarios for public by services by government and etc. It can also be implemented in environment like soil moisture, air quality, the temperature and humidity index. These all things are we are going to see in the further of this PPT. Sensor-enabled devices can help monitor the environmental impact on cities, collect details about sewers, air quality, garbage. Such devices also help in monitoring wood, rivers, lakes, and oceans. IoT can be accessed from anywhere of the world where the internet connection can be enabled. IoT environmental monitoring applications usually use sensors to lend hand in hand with the environmental protection. Nextly, I would like to introduce AQI, which is Air Quality Index, and why is it so important? So as you can see over the right side of the screen, there's a AQI index. So basically AQI is a yardstick, you can say, which ranges from 0 to 500. It denotes that from 50 to 100, it is breathable air. Like 50 to 100 is very normal air. Above 100, like till 200, it is like a caution sign would be there for you. And about 200 would be very dangerous to breathe in. So air quality is measured in ppm. Basically, we measure carbon monoxide and carbon dioxide in air quality index. We use in hobby type sensor, we use MQ series sensors. basically a MQI 135 sensor for carbon monoxide and combustible gases. It is essential to know the air quality of your locality for your as it can tell you what impact it gains on your health. Air quality is an outcome of complex interaction of several factors involving chemical reaction, meteorological parameters, and emissions from natural and anthropogenic sources. Next, we move on here. So, what is IoT-based AQI monitoring system? So, this is our project basically. So, here is our IoT-based AQI monitoring system. As you can see over there, over here, we have used a MQ135 sensor, and earlier, as explained by Sir, we have used a Node MCU, which is a ESP8266 Wi-Fi based module, and also we have used a Node OLED display to display the ppm readings, the air quality readings. We are also using so taking advantage of Wi-Fi. We are collecting this data over our cloud server, which is a ThingSpeak server. So in this project, we have a IoT-based air quality index monitoring system, which monitors air quality index over ThingSpeak. A main advantage of ThingSpeak would be there is an like in any circumstance, the data would be saved on the server no matter what happens. But only thing is you should like continuously have an internet connection over there. So next we'll see how does it work. So these are the components we have used. We have used a Node MCU, which is a ESP8266 based Wi-Fi controller, basically a Arduino embedded with a ESP Wi-Fi module. We have also used a MQ135 type gas analyzer. We'll later on see why did we use a MQ135 gas analyzer. We have a OLED display and a ThingSpeak server also, just to monitor and collect data. Like the OLED display is just to display data. The unit of this air quality index would be in ppm. So this is a circuit diagram. So this MQ135 sensor works on both logics, that is TTL and analog. So in TTL, you have to connect it on digital output, and if analog, in this scenario, we have connected it through an analog signal, and we have a I2C based OLED panel, which enables us the serial clock and serial data communication. So how does a MQ135 sensor work? So basically, first I'll tell you like what all gases it can measure. It can measure ammonia, nitrogen, oxygen, alcohol, aromatic compound, sulfide, and smoke. Basically, all type of combustible gases which can catch fire. So it is for air quality monitoring application, as I said. And there are two outputs, analog output and a TTL output, which can be accessed by turning the potentiometer on the backside of it. This sensor has a long life and a reliability and the reliable stability as well. So let's see a demonstration video of our project. Yeah, so yeah, just a second. So as you can see over here, this is the OLED. This is our project on the left side of the screen, and on the right hand side of the screen, we can see the ThingSpeak monitoring ThingSpeak server interface. Basically, it's a line graph with some information. So the stable reading, like the sensor has a shoot up value till 20 minutes, and after 20 minutes, it gives a stable reading. This data can also be accessed through that OLED panel. Yeah, that's it for this project. And then we have, yeah. So next we have temperature and humidity. So first of all, let's see what is temperature and humidity. So temperature can be defined as the measure a set standard to measure warmth and coldness. It has several units, and there's a lot of discrepancy in units. So basically, the main units we used are Fahrenheit and degree Celsius. So here we have used a degree Celsius. And then we have humidity, which refers to the amount of water vapor or moistures in the air. Within the context of the workplace of health and safety, maintaining suitable air temperature and humidity levels is necessary in order to sustain employee health, comfort, and productivity. In relation with the humidity and temperature concept, there's a simple formula. Basically, the temperature and humidity are inversely proportional to each other. If the temperature increases, it will lead to the decrease in relative humidity, and if the temperature decreases, it will increase the humidity. Yeah, so that is it for temperature and humidity. So let us see what is our IoT-based thermohygrosis system. So basically, as you heard me earlier, so what was AQI, and we had application on an AQI device. Then we have temperature and humidity, and now here's the application on temperature and humidity as well. So earlier, as explained by Sir, we have used a DHT22 sensor, which has a sort of industrial grade accuracy level. So in this project, the thermohygrosis system in which we will monitor the temperature and humidity. This is directly connected to our ThinkSpeak server, our cloud server. So basically, you can access the data from anywhere of the world. The only thing you need to have is an internet connection. And the main advantage of it can be measured through anywhere of the world. Next, we have what all components we used. As said earlier, we have a Node MCU. Sorry, there's a typo here. So it's not a MQ135 gas analyzer. It's a DHT22 type sensor which senses temperature and humidity. And again, we have a ThinkSpeak server which collects our data and also has a graphical interface. So next, this is our circuit diagram. As you can see over here, we have connected the sensor to a digital output, and we have given the power supply to it, like the positive and negative plus 5 volts. So this is the working of DHT22 sensor. So there are two components here, a humidity sensing component and a NTC temperature sensor thermistor. Basically, it's a thermistor for temperature and a normal humidity level indicator for a humidity levels. So DHT22 is a basic low-cost digital temperature and humidity sensor. It uses a capacitive type humidity sensor and a thermistor type sensor to measure the temperature. The data can be accessed in a digital format. For humidity, it is 0 to 100% of RH with accuracy of 2 to 5% of accuracy. And for temperature, it is minus 40 to 80 degrees Celsius. And it has accuracy of plus minus 5 degrees.
Shreyas, just requesting you, just conclude in next 2-3 minutes.
Yes, ma'am.
As we are very, yes.
Yeah, ma'am. So here's a demonstration video of it. Yeah. So over here you can see our again ThinkSpeak server. It has a interface. Here we have also introduced gauges to indicate the temperature and the humidity level. So humidity is in percent RH and the temperature is in degrees Celsius. And also it has a line graph above it. So we'll move ahead as we have time constraints. So now I would like to hand over this presentation to my colleague, which is Saurabh Dubey.
Am I audible?
Yes, you are audible.
Yeah, so this is our main point. How does temperature affect soil moisture? So basically, temperature plays a major role in our environment. So as we know, weather is a short-term part of climate. Certainly, there are very weather cycles which affect the environment, particularly the soil. So the soil can be dried out due to very various situations we know, and so we can rearrange it, whether the condition is droughty or windy or weather or any other climate. But if it is dried out, it affects mainly the growth of the plant. And as we all know, it is reduced if it gets low water and everything else, which reduces the stability of the surface layer and allows more and more erosion, which is very harmful for the environment. And as we all know, erosion plays a major role in stopping the growth of the plants. Soil moisture is important for forecasting both temperature and precipitation, as it plays a major role. And the temperature rises, the evaporation rate of soil moisture increases and leads to erosion. The increased soil moisture evaporation helps to keep the ground cool, and thus it reduces the soil moisture level.
Saurabh, just you can skip the theory part and go to demo directly.
Yes, ma'am, sure. So this is our initiative. This is the project we have made, and it is what is an IoT-based soil moisture monitoring system. We have used a capacitive type soil moisture sensor, as we can see. It provides us the reading of the soil moisture level, and to display the reading in percentage, we have used an OLED display. And basically, the soil moisture is in percentage. It is also displayed on a ThingSpeak portal. So we have, as my friend informed earlier, that we have connected the sensor and our circuit to the ThingSpeak portal using internet. And the main and very important advantage is that it is all saved in any circumstances. These are the components we have used: Node MCU, and specifically we have used a Node MCU 8266, which provides with internet connection, and a capacitive type soil moisture sensor, which provides us with the input, and an OLED display, and the main important part, ThingSpeak server, which specifically displays the measurements. This is a circuit. The capacitive soil moisture sensor is connected to the microcontroller at the input device, and we have connected the OLED display using the I2C protocol. So how does it work? How does the capacitive type soil moisture sensor work? So it basically works by measuring the changes.
You can directly go to demo. Okay.
Yes, ma'am, followed. Yeah.
Followed, ma'am.
Ma'am, the next slide is the ending slide. So that is it.
Yeah, that's fine, ma'am. So it measures by changes in capacity, which is caused by dielectric of soil. As we all know, water does not conduct well electricity. Pure water does not conduct electricity well. So instead, it measures the ions dissolved in the moisture, and these ions and their concentration can be affected by a number of factors, as we all know, means adding fertilizer and all. And capacitive measuring basically measures the dielectric that is formed by soil and water, which plays the major role. So let us take a look at the demonstration video. These are demonstration video.
So as you can see over here, we have a capacitance type soil moisture sensor dug into the ground. So as the ground was well watered, it is showing the percent level in 100%. But if you want more specific readings, you can access the cloud server and have like above 100% readings, which would range up to 200 or 220. So that is it about the demonstration. So thank you for listening. This project was an initiative by Node IoT, and the presenters were Shreya Shawat, Prem Bauskar, Tushar Sharma, and Saurabh Dubey.
Thank you, Shreyas and Saurabh and your team.
Yeah, ma'am.
You have really done a fantastic job. It's really nice. Congratulations to you as well as team. Thank you. Now we will move to the next segment, next session. I would like to invite Mrs. Smita Khandage ma'am, Senior Lecturer, Instrumentation Department, to introduce our next speaker, ma'am.
Okay, thank you, madam. So it is my immense pleasure to introduce our next and last speaker of this 27th National Conference on Sensors and Automation, Mr. Sanil Dalvi, sir, who will enlighten us on the topic Sensors Application in Process Automation. Mr. Sanil Dalvi, sir, has a great expertise of 20 years in industrial automation field and currently working as India Product Head at Emerson for past 12 years. Previously worked with reputed organizations such as Honeywell, Forbes Marshall, and Wipro. He is a core expertise in flow fiscal metering system, dealing with industry vertical like oil and gas, refineries, chemical, pharma, petrochemicals, metals, and many more. We are indeed thankful to you, sir, for accepting our invitation in the midst of your very busy schedule. Once again, warm welcome to you, sir, and over to you.
Smita madam, thank you very much. Can you please confirm if you're able to hear my voice?
Yes, yes, we can hear you.
Okay, let me share my screen and
Yeah.
let me just begin. Okay. My screen is visible, ma'am?
I think it will take.
Yeah,
yes.
I think now I think
Yes.
should be right.
Yes, yes, we can see us.
Okay.
Okay, sir. Thank you, sir. Yeah,
Yeah.
please.
Okay. So I think it's you said I'm the last speaker of this session, and looking at the time, I think I don't know. People are just way past their lunch time. How much would they want to? We'll try and cover as best as we can. So ma'am has given my introduction, so I'll not waste some time on that. Let's begin. This is just a quick safety moment that I am compelled to give you from an Emerson standpoint. Wherever we make a presentation. Start sharing my video as well. I think we can that would be also better. Okay, so this is a safety video or a safety moment that we take. This is a COVID safety triangle. Maintain kind of 2 meter more than distance, not more than 15 minutes within a close vicinity, and always wear your mask. Okay, and always sanitize your devices and laptops and phones and everything. Let's just give you a few seconds of glance of what Emerson is. So Emerson is a global, automation player. We are, it's a US multinational. We are based over the world. We have about 75,000 employees globally, more than 200 manufacturing locations. We hold a large number of patents in the industrial. So we are a hardcore industrial automation player, and many of the products are kind of cutting edge, and we have given it to the industry. And it has been more than, it has been there in the business since 1890. So more than 100 years now. So a very strong company in the field of automation. So I'm very happy to work there. Okay. The slides are taking some time. Okay. Let me just take you guys through just the basics of elements of process automation. I heard a couple of the last sessions that were actually going on. I really appreciate the project that the students have done. Also, the people who had presented. What Emerson deals is with the core industry automation, all related to the process automation side, where that in instrumentation field, you have three basic stuff, right? One is about sensing, second is about control, and third is about final control. So what comes under sensor technologies is the measurement of pressure, temperature, level, flow, density, viscosity, and many other parameters which are there. All these inputs essentially go into the control system where you have some logic. And control system could be like a DCS, PLC, it could be a standalone controller, the batch controller. There could be hybrid systems and other stuff. So, and then you have final control elements like valves and VFD, which is a variable frequency drive, a solenoid valve, on-off valve. We're not going to get into that. We are going to focus only about the sensor technology today here, because the subject, each of them is very broad subject to be discussed. And today, I think I will try and just touch upon the surface even with these sensor technologies. I will. My objective here is to give you some sense about the applications, make you a little bit familiarized with what all the sensors are available on the industrial scale, industrial space. So let's go by. Let's just move ahead. I will spend some time to explain about what all industries that instrumentation deals with, or rather what all and what kind of applications are there. It is too broad a subject to talk. For example, let's start with oil and gas. Okay, within oil and gas, I do conduct internal training sessions for our Emerson team, So this session for application itself is half a day just on the oil and gas, a half a day or almost like a 1 day session. It's that much in depth. But I'm just going to touch upon, I'm just giving my view is that students should have a perspective about how big instrumentation is, how much it affects the overall industry, how much it, how much it impacts the overall, core industries in a ways to grow the economy, and how automation helps to increase the production, enhance the safety, and many other aspects. Okay. So for example, let's take oil and gas. So you have, if you know oil and gas, what we mean by is upstream, or it is also referred as exploration. Okay. So it is a production of crude, or it is production of NG, which is natural gas extraction, right? There are a few more elements to it. There is shale gas, there is coal, CBM, which is coal bed methane gas. All of that comes a part of exploration. What is the instrumentation that is required there? You have wellhead automation. So whenever oil is extracted from oil field, okay, it has to be, it comes out with some pressure, it comes out with oil, it comes with water, it comes with sand, it comes with a lot of chemicals that are injected. All of that comes. So it is all about pressure management, what you're injecting and what you're getting out of the well. So there is a lot of automation that goes in there. It's all about pressure, temperature. There is a pressure to be maintained even at the downhole, wherever, from where the oil is being extracted from the reservoir. Okay. Then once it is brought out, then you have separator, where the oil needs to be separated from the water, the sand, any other precipitates. It has to be done. So separator automation is one. Again, what is required? All of this: pressure, temperature, level, flow, all of that. A lot of chemicals are required to be injected. Steam is required to be injected. Water is required to be injected into the reservoirs to ensure enough pressure is built up in the reservoir for the oil to come out. Then after you have the oil coming out separated, then it has to be transferred, it has to be processed before it goes to the next segment, which is the refinery. Okay, lot of applications here. This is just, it's not even scratching the surface here. Okay, many applications here. Let's come to refinery. So refinery, the oil which is produced by this oil and gas companies, like which are the companies here? It's ONGC. Okay, so they will Kane Energy, or which is now called Vedanta. So they will do Oil India. So they will explore oil and they will send it to refinery. What does refinery do? Here again, it's a big topic. But refinery will accept the crude, do some treatment on the crude, then it goes into the distillation column. This is a CDU, vacuum distillation column. There is a hydrogen generation unit, there's a hydro treating, there's alkalization. All of these are individual big processes by itself within the refinery. And all of these will need all sorts of sensors and parameters that are required to manage the process. Okay. Then you have, once from the video, the crude oil is actually, from distillation column, you have multiple grades of fuel coming in, like you have petrol, diesel, kerosene, naphtha, LPG, it's all coming out of that. Then you have blending. So what is the mix of petrol that you want? What is the octane level? So there are multiple things that are added to that. A lot of automation around that. Then it has to be stored. Like once it is produced, the oil is produced or the diesel is produced, it cannot be just shipped out. It has to be managed. It is kept in tanks. Then it is supplied to the next part, which is the terminals. Okay, which is called terminals and depots is what is called as. I'm just giving you terms because these are very industry terminology. So you can pick up some of this from the presentation. These are called terminals and depots. So refinery, whatever they make, they transfer it to the terminal. Which are these companies? Refineries: HPCL, BPCL, IOCL, Reliance. All refineries which refine the crude to make usable products. So it comes to terminal where it is stored, and from the terminal it is moved to your petrol pumps. So it comes in form of tankers, right? You must have seen these tankers on the road carrying petrol, diesel. So sometimes it is transferred through pipeline. Sometimes most of the time it moves through. So there's a lot of automation around that. How much you are filling, how it is moving. There is a lot of automation that level measurement is happening at a petrol pump. It is happening for the tank. It is happening how much amount of fuel is being filled up in the tanker, whether it is, because it's all related to money. At every point there is money transaction happening. Okay. Then whatever is a balance which is not so much usable is sent to petrochemical where cracking happens. Okay, naphtha is being cracked to produce all polymer products like LDP, HDP, PP. Where is this used? This is all into the plastic industry, automotive industry. A lot of plastic is being used. huge opportunities for automation and industrial space, because the huge complexes, industrial complexes of massive scale. Okay, for just to give an example, one refinery can have about 10,000 pressure transmitters, 15,000 temperature transmitters, like 200 flow meters. It is of that size, what we talk about. Okay. Next is very interesting subject, and this is what initiative I lead for Emerson for India, is for the chemical. We have organic, inorganic, agri-chemical. What are the companies here? So, or what are the products that you must be using? Here it's like all kind of soaps, shampoos, sanitizers, cleaning products. Then talk about it goes agricultural, the pesticides. That I'm sure you don't use it, but it's used in the agriculture industry. So fertilizers, so all of that. Then you have specialty chemicals which produce, like carbon black, which is used as a product in the tire manufacturing, a lot automotive company. Then you have paints. This list is endless, guys. And I'm telling you, each one of you, whoever is using any sorts of products today, everything is associated with chemical or all of these core industries. Okay, so these are the industries which are listed to drive the economy. They are the core industries. Come to food and beverage. India is one of the biggest, milk producer country in the world. So dairy business is huge. Where do you use automation? You need again a measurement of density, there's measurement of viscosity, there's measurement of flow, how much is being collected, where it is being transferred, temperature measurement. All of this happens in a huge dairy industry. Okay. Then come to fact about distillery. So for the sake of students, let us say it is it's about beverages, but by and large it's a huge market again. Many players into the into the industry. Similarly, you have edible oil that you use. It's like a refining process. Edible oil, we have seen a lot of edible oil plants. If you happen to go there, you will stop consuming edible oil, which is like your refined oil. Okay. Sugar, packaged food. Look at pharma. Bulk drug is what I talk about. Tablets. Tablet manufacturing is again huge. Okay. Tablet coating is one application that we do. Formulation is where you have syrups and other things, or you have injections and those kind of liquids which are to be formulated. All of these things need massive amount of automation. And what I mentioned to you about the parameters, you have all those parameters: pressure, temperature, level, flow, density, viscosity, all of those parameters everywhere. I'm just giving you an expansive view of where already you. Metals and mining, metal ore, it has to be refined, right? Metal ore, it just cannot be, you just extract, for example, bauxite. Bauxite is not useful. Bauxite, you need to convert it into an aluminum refinery, which will convert into useful alumina, very similar to a steel plant. They will have a lot of processes there, Automotive, engine testing, right? In average of a vehicle is found out by, declared by, like, it will give you 25 kilometers per liter or 22 kilometers per liter. This is done by some agencies, government agencies like ARAI. All the manufacturers are required to give the numbers, state the numbers of their engine. So what do you think will be under test? The engine, the airflow, the fuel rate, what is the combustion, what is the exhaust, what is the emission level? All of this is getting measured. So engine testing. What is the efficiency of the engine? What is the combustion performance? Whether the emissions are under control or not. So all of this, a lot of applications there as well. Because these are very low flow applications, but industrial grade. Yeah, also very similarly to tire manufacturing. Power again for turbine steam generation. There are a lot of pressure temperature requirements there. There are a lot of vortex flow meter required for steam. Then there is fluke, FGD slurries and all. So there is, each industry is a very deep topic. I am just kind of giving you an idea as to where all things you can imagine and automation and applications can be. Okay, let's see within this industry what are the kinds of applications. Okay, what does the industry expect generally from instrumentation company or from a consultant, or if there is any, if somebody will ask you what are the kinds of applications. So fairly it's about temperature, pressure, level, flow monitoring. They want to just monitor. Similarly, you can do a control of all of this with the density, viscosity, gas detection. By and large, there are kind of two kind of processes. One is a continuous process and other is a batch process. So one needs to understand that which one is a batch, which one is continuous. For example, refinery is a continuous process. It doesn't work in batch. But a paint industry is a batch process. It is based on a recipe. So there are multiple solvents get added. Pharmaceutical, by and large, is a batch kind of operation. Fertilizer also predominantly a batch kind of operation. They build a certain batches, and there is a recipe. So what needs to be added to form the final product? Blending is something again very used at multiple places in the industry, be it paint, chemical, or refined products. Loading, unloading, very common application, could be related to all, because there is a lot of chemicals and raw materials and final products which are manufactured by one company. Okay, raw materials are manufactured by some company, some other company. They have to be shipped out to another company which is using them as a raw material. So there is a lot of transfer that happens. So the loading, unloading, when I talk about loading, unloading, refer this as liquid. Okay, it's not about packets of it's not like your Amazon boxes that come in and go out. It is liquid. These are hazardous chemicals, petroleum chemicals, raw materials which go from one company to the other company. And 15 different chemicals will reach one company. They will further process it, make a final product. Then that will go to some other place of packaging, drum filling, whatever it is. It can be brought in from a ship. It can be brought in from a tanker. It can be brought in from a pipeline. There are n number of ways. So there are right now, the Prime Minister is talking about the hydrogen economy, right? So everybody in the industry is talking about hydrogen, green fuel. There is a hydrogen production. That there is going to be a hydrogen transfer pipeline across the country. And then, so it is loading, unloading. In that case, is a gas loading, unloading, which is what is happening with the natural gas today. Okay, natural gas is getting imported through in form of a LNG, right? It is in the form of liquid form. It comes through the ships, then it reaches our ports. Then you have unloading. You unload the LNG, you store the LNG, and you convert it into a gas, which is called liquefaction, or rather, it is called gasification, regasification. Then you further send it to people like GAIL. GAIL is a company which will transport the gas across the country. Then you have then you have people like Mahanagar Gas in Mumbai and Thane, where they will take the gas and half of it will come to your home for your cooking purpose. Half of it they will give it for your vehicle fuel. That's how every point is a transaction point of money, right? This all has to be measured, metered, transacted. There are some regulatory norms around it. So it's a very vast subject. Look at custody transfer, exactly what I mentioned. Wherever there is a point of money which is exchanged because of this application, it is a custody transfer application. We are transferring the ownership of your goods to another one. So there is a payment money involved in that. Then there are other applications like concentration measurement, net solid content measurement, net oil computing. And there are various. I'm just kind of giving you a glimpse of it. Okay, so let's move on. Let's take a view on how is the process industrial automation of process. So this is where you had a kind of pneumatic automation, where you had a lot of pneumatics involved. When I started in 2001, this was already phased out. Electronic transmitters were already in. There were some elements of pneumatic I2P converters and all. Even they are there still today, but they are not massively. So we have moved from an electronic era, which was the smart devices. What I mean by smart devices, it had some basic diagnostics. Okay, all of that. This is an indication of a pressure transmitter here, but pressure, temperature, all of these from from sensors and transmitter. When I look at it, we don't talk about sensors. When I talk or when we refer in the industry, pressure is one device, the field device, which is a combination of sensor and the transmitter. Only sensor has got no meaning to the industry. It has to be a process signal. It has to be a meaningful signal. It has to be a smart device, right? So this was the era which moved on from like 95, 96, which is still continuing. Then it moved on to the digital protocol, okay, which had HART. So HART, Foundation Fieldbus were all started with Emerson, and we gave it to the world opened the patent for all so that industry can use it. So your DeviceNet, Profinet, Ethernet is something which is a transition phase even now, I would see. Then we have moved on to the IIoT, where you have wireless HART, and now people with all these kind of smart devices, there's a lot of data available. But now the industry expectation is for advanced diagnostics, predictive alerts from the instruments. Okay. Artificial intelligence give us an view. Okay, if there is some alert which is happening, some process parameter has gone bad, it needs to tell you what is to be done. Okay, just not give an alert. There is some problem. Okay, give a problem, report a problem, but also tell a solution, or give some kind of 3 options that it needs to be done. So this is what people are expecting. Industry will move forward in this direction. Then there is something kind of a machine learning. It needs to understand for a pump. Okay, what is the health of the pump? You can measure its vibration, you can measure the noise, you can have acoustic sensor, all of that, and then you have to build some intelligence around that to do a predictive. Okay, do I need a maintenance for this, or can I shift the maintenance cycle? Do I need a replacement of seal? So all of this information is where the industry is heading towards. Okay. Let's look at what it was earlier. So here you had in 420 era, you had only process variable and safety. When it came to heart, you had few more options available. What was, you may ask, what is the advantage? When we moved ahead on the evolution cycle, what was the advantage that you gained? With heart and all, with digital communication, you have some remote configuration capability. One pair of cable can carry multiple information, like on the pressure, it can carry some diagnostic information. On a flow meter, it can carry data for flow, volume, flow, it can carry density, it can carry temperature, all of it from only 2 wires. You can do a polling of that data from the heart. That's where it has a multi-variable capability and an advanced diagnostic. Later on came foundation field bus and Profibus. These are kind of bus architecture. What it provided was, apart from all of that, it gave an easy startup and easy commissioning. Just kind of multi-drop it, get it connected. But additional advantage that it provided was control in the field. Like each device could have a small PID block wherein you can program and which it can take action on itself without going to the DCS. Okay, that was called control in field option. However, I would like to inform that foundation field bus and Profibus has really not picked up in the industry the way it was supposed to be. By and large, the industry is still on hard and happy to be on hard. There are various reasons for this, but this is not a forum for that. But just as a comment that you might want to register. Then you have something which is a wireless, wireless communication device, self-organizing. You have multiple devices in the field. Each one talks to each other and will ensure that the signal is reaching the gateway, and from the gateway it is reaching to the control system. It is cable free. One thing, this is not yet, this is advanced, this is good, but this is not yet for a control application or very fast control. This is good for kind of monitoring purpose. This is where the industry is moving toward the digital infrastructure and digital transformation. Most of the industry is talking about that. And this is where the evolution of industry or IIoT is. So we are on the brink of that. Okay, these are the buzzwords in the industry. A lot of companies want to keep their communication in and around the digital transformation and IIoT. And there are only few companies who really do have proper solutions for that. Okay. Quickly getting on to the sensors. I think pressure, temperature, you guys have heard from the earlier lectures and all, but these are the industrial grade. Have a look at it. There are 3 kinds: absolute, gauge pressure, and differential. I hope you understand the difference between all 3 of that. So I'm not getting into that, but let's have a glance through. These are the pressure transmitter. This is the pressure transmitter with a wireless. These are all industrial grade. So whatever I am showing in my presentation, this is all industrial grade. Because in the previous sessions, I heard something related to hobby sensors and all. I am not able to associate with that. But yeah, this is all industrial grade. So you have, so it can be used for pressure. It can be used for level measurement. How? Because you can use a differential kind of pressure, understand what is the height, and then with that you can kind of derive at the level. Flow meter, you kind of to understand how flow meter can be how flow can be measured by pressure. You have a differential pressure measurement. It needs to create a differential pressure across the 2 points, and then you can pick up the differential pressure. You know the size of the internal ID of that of the pipe, and it's a kind of calculated method to arrive at a flow. It is not measuring the actual flow. I think I'll skip this slide. Yeah, how it works just for sensor for industrial grade. So it uses an isolating diaphragm on which the pressure is inserted from or the process pressure is, once the transmitter is installed, the process pressure is exerted here on the 2 points. This is a differential pressure diagram or internal part. There's a capacitive sensor here. There's a fill fluid which carries the pressure. Whatever pressure is exerted here on the diaphragm, it is pushed through using this internal fluid, which will transmit the pressure onto the diaphragm based on the change in the pressure. You will have a signal. This is a capacitive type of a sensor. Okay, so in case of differential, both of this will be connected to two different pressure points. In case of normal, one will be connected to atmosphere. You can see this point, right? Manifold is there. One is connected to the process. Another is also connected to another kind of process. It will give you differential one. One is connected to process. Other one is connected to atmosphere. This will give you gauge pressure. One is connected to process and internally it is connected to vacuum. It will give you absolute pressure. That's as simple as that. Okay. Let's move to temperature. On the electrical side, you have RTD and thermocouple as a sensor. I think people have in the past sessions have touched upon this subject, so I'm not going to do. But what I need to inform you is there is RTD and thermowell as a basic sensor. Then you need a temperature element which is like this RTD, but you need an element which is a thermowell. You cannot put this RTD in a 100-degree or a 300-degree temperature, in a blast furnace in a stainless steel plant or in an in a refinery or in any of the food and beverage. You can't put sensor. It has to be inserted in a thermowell. Okay, so there's a temperature is sensed on the thermowell, which is picked up by the RTD. Then it gets connected to the transmitter, which are of these types. Okay, you have a single band, multi-band, 8 input. You can receive 8 inputs from. So it is multiplexer. Then you have few other, but essentially these are all temperature transmitter, which will transmit either wirelessly or on 4 to 20 milliampere on HART or on foundation bus. Okay. Let's move on to our flow products very quickly. There are various kind of flow products which are available. We saw this kind of differential pressure. I'm going to talk to you about Coriolis because this is my product. I am India head for a couple of these products here. There's a turbine flow meter, there are RPD meter, there's a magnetic flow meter, there's vortex flow meter, ultrasonic flow meter. These two I'm going to avoid because they are too complex to talk about right now. This is multi-phase flow meter for oil and gas upstream. And a water cut meter is to understand what is the percentage of water in an oil which is produced from the oil well. Then density, viscosity. I'll just touch upon these things. Okay, let's move forward. Coriolis is something which is not really, even after 40 years in the industry, and in India at least 20 years, 25 years, this product has been there in the industry, but it is not really, nobody really, I would not say 100% of the people would know exactly how it works. Okay. So let me take a few minutes to explain to you. I think if you are able to take something out of this equation, out of this presentation, I'll be happy with that. So one of the things is that all the things that I told you, sensor, they are all single variable. So pressure will give you only pressure, temperature will give you only temperature, density will give you only density, viscosity. Okay, level will give you only level. Coriolis is one such meter which gives you multi-variable and it measures it measures mass flow, it measures density, and it measures temperature. Then you have many more parameters which you can further calculate: volume, concentration, percentage solid, lot many things that you can do it. You can calculate. So just understand this is multi-variable. I don't have too much time, I suppose, but let me just go through. This is the gentleman who actually invented the Coriolis force. I'm not talking about the meter, just the force. Coriolis force, which is existential in nature. Okay, so this is all you know, that the Newton's laws are in inertial frame of reference. The Coriolis force is actually when a body is in motion and in a rotating frame of reference. That's where the effect of Coriolis is. Where do you see this effect in nature? When you have a flight which takes off, it will swirl. You look at the movement of the clouds, they will swirl because the rotating frame of reference is the earth. Okay. If a football is kicked at a decently high, with a decently high velocity, it will swirl in the air. Okay, that is the effect of Coriolis. So as much amount of credit you can give it, to Beckham, because he bends it that way. But there is a big element of Coriolis force that is involved, but he understands that and he knows how to use it. Very similarly, we have used that to build a flow meter. Okay, there are some internal parts of flow meter. Just glance through, no need to get into too much of detail. There are two tubes inside. Once the flow gets inside this, it's split into two parts. Inlet on the inlet side, comes out from the other side. Simple. Okay. Then you have something which is called as a electromagnetic coil. Electromagnetic coil, you guys know, right? So this is where you give the electrical current and convert it into a mechanical oscillation. So I am making this tube oscillate at a natural, very close to resonant frequency. Period. Very similarly, you have electromagnetic coils on the left and right placed here and here at both places. What it does, it picks up the mechanical deflection, converts it into electrical signal. Ulta karta hai barabar. Okay. Then you have an RTD and case, and this is for signal conditioning. There are two important factors that are there to have the Coriolis effect. One, the object has to be in motion. In this case, what will be? Any liquid, gas, it is moving with a certain velocity. That is the object in motion. Okay. The rotating frame of reference are these flow tubes, which I am making it to oscillate. Right? Under this, what happens is you have this. This is actually powered on, but there is no flow. So they are oscillating. The tubes are oscillating at a resonant frequency. So the signal coming out from the left and right, which I told you, they are in sync with each other, like almost overlapping each other. What happens under flowing condition? There is the effect of Coriolis, which is felt on the tubes. That is where you have a shift in this signal coming out. What we measure is essentially this shift in the phase in terms of a microsecond of time. That is being used to convert, understand, or other, for the mass flow rate. Okay, little complicated, but yeah, that multiplied by time gives you mass flow total. Okay, let's move on to magnetic flow meter. Okay, before I do that, Coriolis flow meter is very, very widely used because it is used for oil, it is used for cryogenic liquid. When I mean cryogenic, up to minus 196 degrees, it can be used up to 400 degrees, very wide range of temperature operation. It essentially, the advantage is that it measures mass, which is independent of pressure and temperature. Okay, all other flow meters measures volume. So if there is a change in the temperature, what will change? The density. What will change with that is volume. But in case of mass, see, I would say 1 kg mass of cotton is equal to 1 kg mass of steel. But what would be the difference in size if I just have to keep it in front of me? 1 kg of steel is very small, but 1 kg of cotton is huge, right? But fundamentally, they are both 1 kg. That is the difference between volume and mass. That is what changes with the, even in case of liquids as well. So change in the temperature changes the density, changes the volume, but mass remains independent of all of it. Okay? That is what is the beauty of that flow meter and widely used in the industry today. Looking at magnetic flow meter, it's very easy. It works. It is a full bore meter. It is all used for highly corrosive liquids, water, food and beverage, pharma, utility, all of that. Okay. Simple law of operating. I'll not get you complicated. It's simple. It is a velocity meter. It will find out what is, if the velocity is higher, there are these electrical coils which are given power supply. So they have a magnetic flux which is being generated, and when the fluid passes through this tube, it actually cuts the magnetic flux, producing signal which is picked up by the electrode. It is very simple. Okay, it's basically volume into the area, or other, it is the velocity into the area. What is the velocity is picked up from the flow rate based on kind of magnetic flux that it cuts, and multiplied that by the area which is already known for the meter. That gives you, that is the basic Faraday law. Okay, so that gives you a volumetric flow. Very, very widely used flow meter. Again, vortex flow meter, it works in a very different way. It's a 2-wire device. It has this internal parts of it. What is the operating principle? You have a shader bar, what is called as a shader bar. Okay. You have a flow coming in from here. It hits this prism body. It moves in alternate fashion. There is an alternating differential pressure that is created across the two parts, which is transferred by the flex. This is our design. Some of the other vortex flow meter might be different, but basically operating principle is the same. Okay. What is actually picked up is the alternating differential pressure because of the vortices which are formed. Okay. That is picked up to find out the differential pressure. Then you do the signal conditioning. put it in electronics, and you have a signal. What happens? Higher flow rate, you will have higher alternating dP. Higher alternating dP, you can convert it to a signal condition, give higher flow rate. Okay. Let's move on to kind of introduction about level. Level, there are 3 or 4 types. One is a contact type radar, guided wave radar. These are, these are contact type. These are non-contact type radar. Then you have ultrasonic, radar, level transmitters as well. There is a switch, vibrating switch. Where is this used? You can insert it on the side of the tank. So if the level reaches this, the frequency will change. It will detect the change of. So change of frequency on this fork is a determination of that kind of level which is hit you. Okay, these are all for these are complicated. You can have multiple 2 layers, 2 different layers. It can measure. So this is for non-contact, where you have very hazardous. You have a tank with a mixer or agitator inside that. There you use these non-contact type radars. Okay, what are the applications? There are. I mean, you would not know about these applications much, but yeah, flare knockout, what is flare knockout and all those things. But let's just say that any big tank kind of level measurement where it is, you have corrosive liquids where contact type is not possible. You have higher temperatures. You have some mixing agitator inside. That's where you use non-contact type. Otherwise, you use a contact type for simple, just that point indication of level. You can also use a level switch. So you can use multiple level switches instead of all these radars. So these are continuous measurement, more accurate. Okay. Then let me tell you about density, viscosity. Very, very important. This is for finding out what is the density and quality of the product that has been shipped out from one customer to the other. These are generally used in petroleum pipeline across cities and across countries. This is for the density measurement, can be used again for the similar application, chemical concentration. It is used with iron ore slurry, coal tar application, cheese manufacturing, ice cream manufacturing, all of that you use that. So the application is very wide. Viscosity meter, again, same very similar applications. Okay, it'll give you output in terms of viscosity. These are very similar. Let's ignore these 2 right now. Then we come to liquid range, what is known as liquid analyzer. So what are those kind of? You can measure pH, conductivity, okay, dissolved oxygen, chlorine. Okay, then you have something like yeah, I mean, so these are all sensors which are used. This is a sampling panel. Sometimes you can take out the sample of the chemical or the liquid to be analyzed, goes through the sampling panel, and then it gives you indication. Sometimes you have this a sensor directly inside the process fluids as well at that operating temperature. What are the applications? You can see pH monitoring, steam plant, wet scrubber, effluent treatment plants, where you have chemical waste. You cannot leave it to the environment or to any other water body. So it has to be treated. So whether the treatment is done or no, how effectively it has been done. So there you have the pH conductivity and other things, right? I have already shared the presentation. You can go through. In the interest of time, I think I'll cut short a little bit more on explanation. We have combustion analyzer. These are gas analyzers. Okay, this is for carbon monoxide monitoring. SOx, NOx is what is called as sulfur, nitrogen, and oxygen, carbon dioxide, ammonia. All of these are into detection. Where oxygen analyzer is required mainly for the combustion. Combustion is generally you need to have an air to fuel ratio. So what is the amount of oxygen or air that is being going? What is the fuel going? So you need to monitor that, because if you don't do that, then you have ineffective combustion, which means you're losing out on the fuel. If on the other side, you may have a lot of emissions. So you need to have at the right point, you need to have most effective and most optimized combustion, but least possible emission. So that's a very delicate balance in most of the heaters like furnaces, heat treaters, and all of that. Okay, boilers, all of that. Where oxygen analyzers are very effectively used. These are the general applications you can see here: catalyst reformers and a lot of utility. Very interesting that you may not have heard about, is very widely used in industry, is about corrosion monitoring. Corrosion is a big problem. You know what is corrosion. Normal steel, if you keep it outside, it will corrode. Now in the industry, people are using in a very hazardous, they're using kind of chemical plants. There are very hazardous chemicals, corrosive chemicals. So what is the integrity of the pipeline? or other equipment or the reactor. So you need to understand what, otherwise it will lead to some safety issue. And safety issue could be about the plant, it could be about people associated with that, right? And companies don't want that. So people want to know what is the health of the of the equipment, what is the health of the pipeline. There are some weak spots. How do you monitor that? So there are some ER pros which is placed inside, and as and when they corrode. So the first thing, if this kind of corrodes, then the pipeline will start to corrode. So if there is a rate at which the corrosion is being monitored. Very similarly, we have a rate. There is erosion. Erosion is nothing to do with corrosion. Okay, erosion is where you have some solid particle continuously going at a high flow rate. It will eat away some part of the metal where you have a bent and all. We need to know that integrity as well. Then there are something which are inside the process, something which are non-intrusive, which is from outside the process. You kind of measure the wall thickness, or you kind of measure the. So these are very. This is not much talked about in the industry. So I thought I'll just cover one slide. So these are the kind of various applications that we see in the industry. My personal view, I think that's my last slide. I think my view is that if I'm able to, you can extract something out of it. I had only two things what I wanted to tell you. One was I just wanted to give you the scale at which instrumentation and automation is today. It is massive. Okay, it covers all industry, and each industry there is a lot of depth. Okay, and there are multiple and there are opportunities at different levels. At industry level, I mean to say at an oil and gas company, or at a refinery, or at any other pharma. Then there are core expertise. You can have an instrumentation as an expertise and know all of this, or you can have an application oriented and know only about one industry, or you can be people like our side who are understanding a little bit of the industry, who understand a little bit about application, and we understand more about our products. What has to be given. So there are multiple opportunities. I would suggest you guys can stay. You can get connected with people in the industry on the. On some platforms like LinkedIn, connect, build your network, reach out to them, understand things, ask them questions. I think by the time you are moving into, you complete your education and they're about to get into the field, you can already build a lot of connect within the industry. And I think people are more than happy to answer questions or get back. Half an hour, 40 minutes is too short a time to talk about anything in detail. I can just barely scratch the surface of what the industry is about. But I think, ma'am, so this is all about it from my side.
Thank you, sir. Sir, there is one question from student. Khandage madam has sent that question in the chat box on behalf of student.
Yeah, let me just see.
Yes. Sir, can you tell few applications of AI and ML in industries? Okay. That is a question.
Okay. So it is not yet there. I mean, the industry is evolving there. Okay. So right now, AI and ML is at it is at a computer level. But let me give you one example. I will give you two examples. It is related to AI or machine learning, whatever you may want to put it across. There are two different subjects. One, let's say pump monitoring system. Okay, we do have a pump monitoring system or application in the industry where we have a vibration, acoustic sensor, pressure, temperature, and flow. All these parameters have been in the industry, and they have been it has been monitored. Some part of it is used for control. Okay, but the intelligent part of it is, if something went wrong with the pump, or if any maintenance is required, or if there is any kind of disturbance in the operation, one of these parameters will get kind of disturbed, right? Earlier, what used to happen is a customer would report, okay, there is some problem, this is not working well. So somebody from our side or somebody from the pump manufacturer will go there, he'll understand. Now what needs to be done is already in the minds of the people. It is somewhere documented with the pump manufacturer or with the instrument supplier or with somebody. Now there is a time where you incorporate all of that and you put it into a program, and you can set some rules. Okay, if the pressure is this much, temperature is this much, but the vibration is out, then this could be the problem. Okay, it gives you that kind of predictive. And then you can monitor this, you can save it into a historical data and see the trend of all these parameters. So it's just not pressure temperature monitoring, it is the overall health monitoring that it has been done for that particular pump, because these pumps are very expensive and they running it in the running plant you don't have 3-4 pumps as alternate, there are one and one standby. Okay, so the whole manufacturing setup can just collapse if something goes wrong. So that is very crucial to monitor. This is one example. Another example I will give you is about my product that I deal with, is about a Coriolis flow meter. Now you may be aware about things like calibration, right? Every instrument needs to be calibrated before they leave the factory or it is manufactured. But there is a point where it has to be recalibrated after 1 year, 2 year, 5 year, whatever time period the user defines. Now, pressure transmitter is very easy because it is not inline. Now, please understand the difference between inline instruments and, what do you say? So what I mean by inline is there is a flowing pipe, or there's a pipe through liquid is flowing or a gas is flowing. My flow meter is sitting on the pipe. It is not outside the pipe. So I will not be able to remove the flow meter, or if I want to remove the flow meter, I have to shut off. I have to take a shutdown. I have to close the process. Valves, flow meters are all inline instruments. So that is why they become more critical. You cannot. Transmitter, I can just shut off an isolation valve, remove the transmitter, put another transmitter. My process does not stop. Similar thing with the transmitter, the temperature transmitter, pH, conductivity, all of this. They will not stop the process. You can replace it by some other, other instrument if something has gone bad. But the flow meter, valves, if they go bad, the process needs to stop. So that is why they're critical. Now, what happens is because of calibration is, so firstly, people don't want to have any stoppages in their production. Second thing, but you need calibration. Now the calibration becomes a headache because sometimes they say that, okay, every year you have to do it. Every year you remove the flow meter, send it to some lab, get it calibrated, put it back there. It's a wastage of time, additional manpower, loss of production, all things are involved. So in our flow meter, about 7 years back or so, what we call as we have a smart meter verification. This is connected to your question. That's why I'm giving you. So there are a lot. So it checks the structural integrity of the Coriolis flow meter tube. What I was showing you about internal tubes and all. It checks the internal structural integrity. It checks all the internal parameters, resistance value. It checks the electronic. It checks the process condition. It checks the effects of the process on the instrument. And it's a 2-minute test which can be done without interrupting the process. And the result is, it gives you a result in form of meter pass, meter fail. What does meter pass mean? That it is perfectly well within the factory specification. Don't need to change anything. But because of corrosion, erosion, choking, blocking, coating, whatever thing in the flow meter, if the meter is not within the specification and somebody runs this test, it will say the meter failed. Now the meter has not gone bad, which means that what it means that it needs to be checked. It now is a time to remove it for calibration. So there are some advanced, one may call it advanced diagnostics, one may call it artificial intelligence, one may call it. So who has come up with this? So the intelligence firstly lies with the people who have spent a lot of years in the industry. Some part of that intelligence which people have gained in the industry, that is being formulated in kind of a program and put into the transmitter programming with certain criteria that, okay, if 1, 2, 3, 4, 5 criteria are met, all right, you can report that the meter is good, because that otherwise people would have done it manually, but now it has been done automatically. But the logic, the programming logic, the criteria, the loops have all been defined by people who have spent enough time in the industry. So that is how there are just 2 examples, but there are many more I can share with you more. I hope I have answered your question, or if you want any more.
No, sir, it's enough.
Thank you.
Sir, one more question. Someone is asking for difference between viscosity
I
and
can see that.
density. Huh?
Density, okay. Good question. You want to know the difference between density, viscosity, or you want to know how it is measured?
Measured
differently. Okay. So, okay, let me just go back and you can see. I will need some time to explain this, but I'll try for it. Okay. So I showed you one sensor for density viscosity, right? It was a fork type device. I'm not able to go back to the slide. I don't know why. Let me just show you that because, yeah. Okay. You can look at this. They are very similar. You can see on the screen, right?
Yes,
This
sir.
is
It
a,
is visible.
yeah. So this is a fork type density meter. Very similarly, you have a fork type viscosity meter. In fact, the viscosity meter can give you viscosity, density, and temperature. Okay. So it's one and the same instrument. Here we have allowed it to measure, here we have restricted it to measure only density by a software program. Here we are allowing it to measure all that it is capable of. Answering a question, what happens is, so this is meant only, only for sake of liquids. Okay. This is not for gas, first of all, and this is not for solids. This is all for liquids. Okay. Now, when you have these times, it is what we call as this fork. Okay, we are making it vibrate at a certain frequency. Okay. Now, so it has been calibrated in air, it is calibrated in water, and some other known density fluid. Okay, so that is the calibration done. So it knows that if any other different density fluid comes in contact with that, what will happen is it will cause a dampening effect. Dampening, it will cause more dampening or it will cause less dampening. So density and frequency are inversely proportional. For example, you have a higher denser fluid that will have more dampening effect on the fork, right? So it will have lesser the frequency, it will reduce the frequency. That's why inversely proportional. For example, if I use it, if I put this in water, it will give you kind of density of water. But if I put this in a very thick, or for example, edible oil, actually oil will have a lesser density, so it will have less dampening effect. But if I put it in something like, let's say any other chemical which has got more density, what it will do? It will have a dampening effect, it will lower the frequency. So change in the frequency is how you detect the density. Now come to viscosity. Viscosity is a little complicated. So the energy that we drive, so now here it's only about a frequency, right? When it comes to density. When it comes to viscosity, so there is an energy that we provide, or rather we monitor. If I have to continue to oscillate this at a certain resonant frequency, I give an energy, for example, 100. Okay. And then I will drive it at 100 by 2, half the energy, these two levels. At these two levels, we try to monitor what is the bandwidth. So the change in the bandwidth actually gives me viscosity. Change in the frequency gives me density, and there's a RTD which measures. I would suggest I can give you more. I have 5 slides to explain on just on that concept, but you can go to our website, just type in this fork type viscosity meter and it's working. There's a good video there. Probably you can you will be able to correlate to what I just said, the bandwidth and other things, and you will be able to get your answer a little bit more there.
Definitely, sir. Definitely.
Yeah.
Thank you so much, sir. Actually, within a very short period of time, you have explained so fantastically. Actually, on behalf of VPM's Polytechnic, we are really grateful to you for this wonderful session. Thank you so much, sir.
Yeah, thank you so much.
Thank you, sir.
Now we will move to the last segment of this conference and most awaiting moment, that is e-poster competition. VPM's Polytechnic has arranged e-poster competition, and students from various institutes all over the Maharashtra has participated in e-poster competition. So let us have a look on these posters. In this e-poster competition, there were 2 sections. One is handmade and few posters were software based. Within a very short time, students have made this such a nice, wonderful posters. And these posters were made on different key areas on sensors and automation. Many entries were there, and now we will see winners of this e-poster competition. So let's see who are the winners. Any guesses? We are there are two sections. One is handmade and another one is posters by using software. So let us see winners of e-posters using software. And the first winner of e-poster competition Yes, it's Tanvi Chiman from VPM's Polytechnic Thane. Congratulations, Tanvi. The second winner of this e-poster competition is, these posters are based on software. The second winner is Chinmay Sawant from Thakur Polytechnic, Kandivali. Congratulations, Chinmay. Next, we'll see the next winners of e-posters handmade. And the first winner of e-poster handmade section, the first winner is Samarthya Vilas Surve from BPM's Polytechnic. Congratulations, Samarthya, for this beautiful poster. The second winner for e-poster handmade is Prachiti Mirashi from Zagru Singh Charitable Trust College. Congratulations, Prachiti, for this wonderful poster. And the consolation prize. Yes, there is consolation prize in e-poster handmade section, and it goes to Tabin Quadri from VPM's Polytechnic Thane. Congratulations, Tabin. Congratulations to all winners of e-poster competition as well as participants. Congratulations to all, and your certificates will be shared in next week. So all of you note that. Now we will move to the last segment of our conference. Before that, I would like to invite Mrs. Rajeshri Patil ma'am, in charge head of electrical power system, to announce our forthcoming conference. Over to you, ma'am.
Thank you, Pooja. Very good afternoon to one and all. I, Mrs. Aryu Patil, in charge of EPS department and organizing secretary of our next conference, take this privilege to announce our next 28th upcoming national conference. I'm glad to announce that our conference topic is on battery electric vehicle and related technology, and it will be scheduled on 5th March 2022. We all are aware that fuel charges are increasing day by day. So in order to address the future mobility changes in terms of impact on environment as well as depleting fuel stocks, electric vehicle technology is the effective mode of transportation. The automotive industry across the globe is gearing up for battery electric vehicle technology. So there is requirement of skilled manpower in this domain. So this conference aims to introduce all participants about our next mobility transportation, that is battery electric vehicle and its related technology. Just introduce that what is battery electric vehicle. It is exclusively use electric motor and motor controller instead of internal combustion engines. They obtain power from battery pack and thus have no internal combustion engine or fuel tank or fuel cell. So battery electric vehicle includes motorcycle, bicycle, scooters, skateboards, rail cars, watercraft, trucks, bus, and so on. The main objective of this conference is to contribute towards healthy and stable environment. So our conference will be focused on the topics like technology using battery electric vehicle, BMS, then converting ordinary bicycle into BEV, charging stations, and role of engineers in battery electric vehicle. Our targeted participants will be students, faculty, industry from any engineering background. The conference will be on online platform, and so there will not be any registration charges for the participants. So all are invited to take this benefit of this our initiative. Further details will be posted on soon on our official website. Thank you very much.
Thank you, Patil madam. I hope that all participants of this conference, definitely we expect your enthusiastic participation in our next conference as well. Thank you so much. Now I request Mr. Tushar Mohite Patil sir, organizing secretary of today's 27th National Conference on Sensors in Automation, to express vote of thanks. Sir.
Thank you, Pooja. So we are in the last segment of the conference. So in last 2 days, we have explored many key areas in the sensors in automation. So we wanted to know sensors in automobile, we wanted to know the sensors in process plant, then the sensors in radar, then LoRaWAN technology. So all the experts, they delivered the excellent talk on their respective topics. So I'm sure all the students, all the participants, they must have gained valuable inputs from the speakers. So I'm very much thankful to all the speakers for sparing the time and delivering the talk. I'm thankful to our organizing committee because the task of conducting any conference, it's very huge. All the organizing committee members, they helped each other and we made it a success. So I'm thankful to all the head of the Department of Instrumentation, Mrs. B. Doshi madam, then in charge of electrical power system, Arya Patil madam, and all the staff from their respective departments for organizing this conference. So I congratulate all the winners of the e-posters because they made the e-posters. They were having very small time to make it because their exams were there, and in that again, finding some time they could make it. So I heartily congratulate all the speakers and the winners of the e-poster competition. So I'm very much thankful to all of them, and I think now the next conference is announced, that is the 20th conference, and we are looking forward to it. And I now thank once again all the members. Thank you very much. And I declare now the conference is over. Thank you.
Thank you all.